please go to www.zoom.us/download. Mohon Bapak Ibu menonaktifkan mic atau mengklik tombol mute apabila tidak sedang berbicara. To help today's meeting run smoothly, please mute when you are not speaking. Jika Bapak Ibu ingin mendengarkan terjemahan dalam bahasa Indonesia, klik Interpretation, pilih Indonesian. Anda tidak perlu pindah channel saat berbicara. Jangan khawatir, pembicara dan interpreter dapat mendengar Anda. If you'd like to listen in English, click Interpretation, then choose English. You don't need to change channel when speaking. Don't worry, the resource person and the interpreter will be able to hear your voice. Untuk pengguna Zoom Mobile, klik More untuk masuk ke pilihan berikutnya. Pilih Language Interpretation. Lalu pilih Indonesian untuk bahasa Indonesia. For Zoom mobile users, click More to go to the next choice. Then, choose Language Interpretation. Then, choose English for English. Mohon dipastikan bahwa Bapak Ibu sudah memilih salah satu bahasa yang akan digunakan. Karena jika Bapak dan Ibu tidak memilih, suara Bapak dan Ibu akan mengganggu pembicara dan proses penerjemahan. Terima kasih atas perhatian dan kerjasamanya. Please make sure that you have selected the correct language for not making any noises for both speakers and interpreters. Thank you for your attention and cooperation. Jika ada kendala mengenai fitur ini, silakan hubungi host yang sedang bertugas atau hubungi IT support. If you have any technical problems regarding this feature, feel free to chat the host on duty. Thank you.
Bapak dan Ibu yang saya hormati, beberapa saat lagi acara Knowledge Sharing and Capacity Building Earth Observation Services for Water and Food Security Planning in Indonesia akan kita mulai. Hari ini merupakan hari ketiga dengan tema Flood and Other Information for the Disaster Resilience Planning. Demi kelancaran pada siang hari ini, pertama-tama kami akan bacakan tata tertib untuk diperhatikan Bapak, Ibu, dan hadirin sekalian yang bergabung secara virtual melalui Zoom. Acara ini disiarkan secara bilingual. Bagi Bapak, Ibu yang mengikuti melalui Zoom, bisa mengaktifkan fasilitas feature yang ada di bagian bawah layar Bapak dan Ibu sekalian. Acara ini direkam dan disiarkan secara langsung melalui saluran YouTube PUSFATJA LAPAN. Peserta dimohon untuk tidak mengaktifkan fitur mikrofon saat kegiatan webinar berlangsung, kecuali diperkenalkan oleh moderator. Bapak, Ibu hadirin yang saya hormati, acara akan kita mulai. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang, salam sejahtera bagi kita semua. Om Swastiastu, Namo Buddhaya, salam kebajikan. Selamat datang dan selamat bergabung di acara Knowledge Sharing and Capacity Building yang diselenggarakan oleh Pusat Riset Aplikasi Penginderaan Jauh, Organisasi Riset Penerbangan dan Antariksa LAPAN BRIN, dengan kolaborasi Asian Development Bank serta European Space Agency. Perkenalkan, nama saya Nancy, dan hari ini saya bertugas untuk mengawal acara pada hari ini sampai dengan selesai. Mewakili panitia, kami mengucapkan terima kasih atas kehadiran Bapak, Ibu, dan hadirin sekalian pada kegiatan yang diselenggarakan selama 5 hari, yaitu tanggal 22 sampai 26 November 2021 secara online melalui Zoom Conference maupun live streaming melalui kanal YouTube PUSFATJA LAPAN. Hari ini menginjak hari ketiga dengan topik Flood and Other Information for Disaster Resilience Planning. Kegiatan knowledge sharing and capacity building ini merupakan rangkaian kegiatan workshop dan training mengenai pemanfaatan remote sensing atau penginderaan jauh dalam mendukung pengelolaan sumber daya air dan ketahanan pangan di Indonesia, serta mendukung sektor penanggulangan bencana. Dalam kegiatan ini juga akan diperkenalkan berbagai Earth Observation Platform Services yang digunakan dalam analisa geospasial untuk sektor penurunan tanah atau land subsidence, monitoring building dan infrastruktur stability, banjir, pertanian, serta marine aquaculture. Sebelumnya, izinkan kami menyampaikan terima kasih kepada yang kami hormati Bapak Kepala Pusat Riset Aplikasi Penginderaan Jauh Organisasi Riset Penerbangan dan Antariksa Lapan BRIN, yang kami hormati para direktur atau kepala dari kementerian dan lembaga dan atau yang mewakili, yang kami hormati Bapak dan Ibu narasumber serta moderator, yang kami hormati perwakilan dari Asian Development Bank serta para tim pengajar, serta Bapak dan Ibu hadirin sekalian yang telah bergabung pada acara hari ini. Sekali lagi kami sampaikan selamat bergabung kepada Bapak, Ibu hadirin serta rekan-rekan sekalian yang saat ini telah terkoneksi melalui jaringan Zoom Meeting dan menyaksikan kegiatan hari ini melalui kanal YouTube channel PUSFATJA LAPAN. Acara hari ini disiarkan secara bilingual, dan bagi Bapak, Ibu yang mengikuti acara melalui Zoom dapat mengaktifkan fasilitas interpreter untuk memilih bahasa yang akan digunakan dengan memilih tombol di bagian bawah layar Bapak dan Ibu sekalian. Saya sendiri akan mengawal seluruh rangkaian acara pada hari ini dalam bahasa Indonesia. Bapak, Ibu, hadirin sekalian, selama beberapa jam ke depan, kita akan disuguhkan oleh beberapa segmen acara tentunya yang penuh dengan ilmu. Pada hari ini, akan diawali dengan sesi pembelajaran atau lecturing mengenai pemanfaatan data-data penginderaan jauh untuk mendapatkan informasi terkait penanganan kebencanaan banjir. Materi ini akan disampaikan oleh para pengajar dari Luxembourg University of Science and Technology atau LIST, serta tim pengembang platform WASDI. Sudah bergabung dengan kita langsung dari Luxembourg, Dr. Patrick Madgon, Dr. Paulo Campanella, Dr. Marco Cini. Karena mungkin di sana masih sangat pagi sekali, mungkin sekitar jam 6 atau jam 7 pagi. So, allow me to greeting you all with a very good morning. Institut Sains dan Teknologi Luxembourg adalah sebuah institusi penelitian dan teknologi yang mengembangkan prototipe produk atau layanan yang kompetitif dan berorientasi pasar untuk pemangku kepentingan yang dapat digunakan untuk membantu pemerintah, sektor swasta, dan publik secara luas, dan bekerja di seluruh rantai inovasi. The Environmental Research and Innovation atau ERIN Department yang ada di LIST mengembangkan strategi, teknologi, dan alat untuk memantau, menilai, menggunakan, dan menjaga sumber daya alam terbarukan dengan lebih baik. Sedangkan WASDI adalah sebuah joint venture antara Fade Out Software atau pengembang perangkat lunak di Italia, RSS Hydro, dan LIST. Visi dari WASDI ini adalah salah satunya untuk membantu memudahkan pekerjaan para ahli dan peneliti pengamatan bumi menggunakan teknologi cloud computing. Setelah sesi pembelajaran nanti, kita akan sama-sama bertukar ilmu dan berbagi pengalaman tentunya dengan narasumber yang juga pakar yang sangat menarik untuk diikuti. Hari ini akan bergabung dengan kita Ibu Dr. Filsa Bioresita dari Departemen Teknik Geomatika Fakultas Teknik Sipil Perencanaan dan Kebumian Institut Teknologi 10 November, dan ada Ibu Hana Listi Fitriana, peneliti Pusat Riset Pemanfaatan Penginderaan Jauh, Organisasi Riset Penerbangan dan Antariksa Lapan BRIN, dan sesi knowledge sharing ini akan dipandu oleh moderator Dr. Firman Hadi. Baiklah, Bapak dan Ibu hadirin sekalian, untuk mempersingkat waktu, kita akan mulai sesi pertama, yaitu pembelajaran di hari ketiga ini, dengan mengundang teman-teman dari LIST dan WASDI. kepada Mr. Patrick Morgan, Dr. Paolo Campanella, Dr. Marco Cini. I offer this time and screen to you, and we would like also to remind you to have a first break for 10 minutes at 2:30. So, Dr. Patrick, time is yours.
Good afternoon, and thank you very much, Ms. Cosmarini, for this introduction. As you have explained, we will focus today on flood mapping using satellite Earth observation data to monitor floods and to assess the impact that these floods have on at large scale. Actually, we will be today to give you an overview of the developments we have made at our institute, and also in collaboration with a private company called VASDI that is going to be represented by Mr. Paolo Campanella. From the Luxembourg Institute of Science and Technology, I'm here today together with my colleagues Marco Cini, who is a Senior Research and Technology Associate in our Remote Sensing Department. And we will be joined also by Dr. Ramona Pelic, who is also a Research and Technology Associate in the same group. My name is Patrick Matken. I'm a group leader in remote sensing and natural resources modeling. I would also like to mention the CIMA Research Foundation that helped us to develop this course that I hope you will enjoy and take advantage of. I would like maybe to briefly introduce the course to show you how we have organized this session. For this, I will share my screen. So we have put together the agenda that you can see hopefully now on your screen. From our side, we will have prepared three.
We cannot see your screen.
No? Okay. Thanks for telling me. Does it work now, Marco?
Yes.
Okay. Sorry for that. So you see now, hopefully on the screen, how we organize this afternoon session. There will be three main presentation blocks that are organized by list. So we will start with a 1-hour introduction to microwave remote sensing, and in particular focus on how this technology can be used for large-scale flood mapping. This presentation will be made by Marco Cini. Then I will continue with a half-an-hour introduction to VASDI and the flood mapping applications that our team has implemented on this VASDI platform together with our partners from the VASDI company. We will have a short break then before having a live session and tutorial to show you how these hazard applications on VASDI can be used. For this, we will have Paolo Campanella from the VASDI company, who will be show us how this works, and he will be joined by Ramona Pelic from our research group to give you a step-by-step introduction on how to use the flood mapping applications currently implemented on VASDI. Then, as it was mentioned already by Ms. Rosmarini, we will have later today a knowledge sharing session where we will be joined by two representatives from the geoengineering department and the Faculty of Civil Planning and Geoengineering from the Institute of Technology in Sepulu, Nopember. And also we will have a presentation from Hanna Listi Filtriana, who is in the Remote Sensing Applications Research Center from LAPAN. So we will be we look forward to also know about the applications that are currently being used in your country. Now I will give the floor to my colleague Marco Cini, who will present you let's say the basics, the theoretical background of the applications that we have developed for monitoring floods in Southeast Asia. Please, Marco, can you share your screen?
Yes.
Thank you.
You have to stop sharing your screen, otherwise I cannot.
Okay.
Oh, thank you. Can you see my screen?
Yes.
Hello, everybody. I'm Marco Chini, and I will give you some information about a basic principle about how to map flood using microwave data, in particular synthetic aperture radar. And all the information are related to the algorithm that we have been implemented on WASD platform. So let's start with a short introduction to the topic. Like we know that flood affects society, economies, and ecosystem in a certain time and place with a devastating impact. And it's forecasted that in 2050, 1 trillion worldwide annual losses for coastal sea will happen. Of course, useful information about flood extent and inunded area can be obtained from a remote sensing platform, either airborne or spaceborne. And this detection of changes of water surface can be used in a variety of different applications, ranging from simple mapping and monitoring of water body to more complex water quality assessment and of lakes and reservoirs. When we map the extent of a flood event, we can use it to evaluate the magnitude of the event itself, and also to validate and calibrate flood forecast modeling. And also it's important to know that while the detection of permanent water body can be done with different kind of sensor, either optical or SAR, the flood event are much more opportunistic. So synthetic aperture radar are better because they are not affected by any restriction due to the lights or the cloud cover. And also, given the fact that sometimes flood has a really rapid recession in small and medium-sized catchment, the weather condition is something that we have to consider. Then synthetic aperture radar is really the satellite that needs to be used for this purpose. Flood is not only the most widespread natural disaster, but is also one of the most frequent natural disaster. Looking to the International Disaster Charter website, it's possible to see that half of the activations are related to flood. And then there is also an increase of awareness regarding satellite-based retrieved information to support crisis management and to support civil protections. Indeed, there is an increase of the literature in this domain in these last decades, and this is due to mainly the increase of numbers of satellites available. In particular, radar satellite to be used. There are many constellations around the world, from national and international institutions. Of course, the extraction of floodwater extent using remote sensing data is becoming more and more important to manage the hazard related to flood and to face the three different phases of it. So alert and preparedness phase, emergency management, and post-event damage assessment. This is and that is also part of the sustainable development goals. In this respect, the Copernicus initiatives, which is a collaboration between the European Commission and ESA, made a big step forward with the Sentinels mission, which is an initiative where there are several different satellites that have been developed and put in place to face the emergency. And their main characteristics is that they systematically acquire images all over the world at different frequency in a systematic way. And of course, for disaster responders, having access to a massive amount of satellite data, it doesn't have an intrinsic operational value because this large amount of data become relevant if they are rapidly translated into maps in order to be used for manage the emergency operation. That's why nowadays it's more and more important to have cloud computing infrastructure to handle this big amount of data, to process fast and to deliver as soon as possible the information. Now let's move to the core of the presentation. When we talk about flood, we have to make a distinction between three different kind of land cover. So bare soil, vegetated area, and urban area. Because from a synthetic aperture radar perspective, detect the behavior of water and the interaction with the microwave signal, it's quite different. So let's start from the transmitted signal on the surface. In case of the so when the water will appear, the backscattering in the three different area will change, but it change in general in a different way. Indeed, for example, let's start from bare soil. So in bare soil, we have a decrease of the backscattering because the surface become smoother, and then we have an increase of the specular reflection. So the energy will be scattered in the opposite side with respect to the line of sight of sensor. So in general, when the flood occurs over bare soil, we see a decrease of the backscattering, and this is the main feature we have to look at to detect flood. In case of vegetation, we have several different scattering behavior because we have the contribution from the top of the vegetation, the main part of the vegetation trunk, and also there is a so-called double bounce effect, which is the interaction between the vertical structure and the surface in front of it. In general, what happened with the flood? That the surface is becoming smoother, so then the specular reflection in the double bounce component will increase. So it means that the backscattering usually increases when the vegetation is flooded. Of course, this is possible if the wavelength of the transmitting sensor is long enough to penetrate the first layer of the vegetation and to give rise to the double bounce effect. So this depends from the vegetation and the wavelength of the satellite. Then we have the urban area. In general, the urban area as well is characterized by the double bounce effect, which is composed by the facade of the building and the surface in front of. Also in this case, the double bounce increase because the dielectric constant of water is higher with respect to the surface, and then we have an increase of the double bounce component. Of course, we have other component of backscattering from the roof of the building, but this doesn't play a role in the flood detection because there is no interaction with the water in front of the building. But as we will see also later, sometimes they just look into the intensity. So to increase of this backscattering value, it's not sufficient to detect flood because the magnitude of this increase is related to the geometrical arrangement between the building and the satellite line of sight. So there are many different components, especially because urban area is really a complex scenario where, of course, you have buildings, but you have... Sorry. So you have buildings, but... So someone, there is a question from someone. So then there is, so urban area is a complex scenario where we have buildings, but also we have vegetation, bird soil, and so on. But we will come back more in detail on this aspect. So how does it look like a SAR image? So here is an example with a SAR image at X band, 3 meters. So quite which is quite very high resolution image, and we can see that this dark area represent the flood. We see that flooded area are quite dark, and the backscattering quite low. Here is the same area, but image with another sensor, which is an MDSat-wise watt sensor at 150 meters. The flood event is the same, but you can see here that so we are able to image a bigger area. So the SWOT width is higher, but the detail and the resolution it's less. And it's important. It's important to see that, for example, that urban area looks quite bright. So the backscattering is quite high because we have this double bounce effect that with this dihedral structure give rise to an high value of the backscattering. But it's important to know that depending on the spatial resolution, also buildings and in general a complex object looks a bit different. Although the water extent it looks similar at X and the C band, and at 3 meter resolution and 150 meter resolution, we see that these bright area, which are, for example, building at 150 meter, are quite bright. While when we move to 3 meter, this is a bit the number of pixels which are bright are much less because there is for example, at 150 meter in the resolution cell, the double bounce is the dominant scattering behavior, while at 3 meter resolution we can differentiate the different scattering behavior from the building. So then we have the scattering from the double bounce, plus we have the contribution from the roof, and plus the shadow area. So then although it's we have much more detail, images become a bit more complex to be interpreted. And here is the clear example that in urban area we have still some bright pixel, but we have also mid-gray level scale pixel plus very dark those from area in the shadow. Again, so here is the image I showed before, and this is basically how the image looks before the flood occurred. You see that where the water is present, which is dark during the flood event, it's quite light gray in the previous image. So the backscattering, it means is higher. And then if you combine the two in a RGB color composition, where we put in the red channel the previous image, and in the green and blue channel the image acquired after the event, the changes in the backscattering appear in red. So in red are area where the backscattering is decreasing, while light blue are area where the backscattering is slightly increasing. This is a representation that I will use along this pitch to highlight which this kind of changes. So here, this light blue could be associated to an increase of the, for example, soil moisture, which make rise to the dielectric constant of the soil. So then an increase of the backscattering. Here again, the same flood event, but a different resolution. So you see here that in this RGB color composition, at the middle of the image, it's possible to see this decrease of the backscattering. Of course, you see there is always a trade-off between the amount of detail in terms of spatial resolution and coverage. This is a trade-off that satellites have to deal with, because in order to increase the spatial resolution, we have to reduce the SWOT width of the satellite. So if you want to image in one shot bigger area, you need to reduce the spatial resolution. So then, but today there are many different missions that can be useful for our purposes. Here, another example of an RGB color composition concerning, for example, flooded vegetation. So as I mentioned before, when we create this color composition, red are areas where the backscattering is decreasing, and this is the flood over bare soil. Instead, blue or light blue area are the area where the backscatter is increasing. This is the case in this area, where we have an increase of the backscattering due to the increase due to the presence of water beneath vegetation. These are rice field, and the sensor is a C-band satellite from Sentinel-1. We have, in general, we see over bare soil a general increase of the backscattering, and this is due to soil moisture, because probably here we had heavy rainy days, so then you have also an increase of the soil moisture. Here is another example, also Sentinel-1 C-band 20-meter resolution for an event occurring in Houston. We will talk more in detail later. This is the image before the event, and this is the RGB color composition with the event during the flood. So it's possible to see that in red, again, we have a decrease of the backscattering, which is over soil. And here, as I mentioned before, are the flooded building, where we see a slight increase of the backscattering due to the increase of the double bands component. Of course, when we talk about SAR data, we have to consider that it's a system active, so it send a signal and then measure the signal sent back to the sensor, so the capacity to backscatter energy to the sensor from an object. But to get the resolution in range, it needs to have a side looking, so it cannot look from the nadir, but he has to image the area with a certain incident angle. This create different effect, and then different kind of distortion of the information that we usually name layover, foreshortening, and shadow. So for example, if we so in general is when we have a small incident angle, we have less shadow, because for example, in mountainous area, the slope not in front of the sensor has less shadow, but we have another problem, which is the layover. So that basically in the resolution cell in range, we have the contribution from object from the same distance, but on ground position in different places. Basically, what we see that is the slope of the mountain in front of the sensor is appearing really thin, bright lines. but we have less shadow. When we move for higher incident angle, the shadow increase. So the side of the slope that the sensor cannot see increase. So here this is the shadow, but we have less layover. So then we are able to sample better the object on the ground and to better position them. And then also there is the foreshortening that appear for slopey area, so that basically the foreshortening effect is higher when the surface is orthogonal to the line of sight of the sensor. Here is an example of Sentinel-1 image. We see here that we have the sea, here is the land, dark area are the are water, and then we have some bright part, which is this layover foreshortening I mentioned before, and in the opposite side we have the shadow effect. In general, looking to this image, it's possible to see that over mountainous area you have bright side on the left, so and darker area on the right of the mountain. So it means that the sensor is looking from this side. Here is what I was saying. So we have here in this part, which are bright, these are mountainous area, is the foreshortening, and in the other side you have shadow. So here are the detail, and of course here we have water. So this is important to know when we deal with the SAR-based flood mapping, because in general we are looking for a region which are dark, where the backscatter is very low, or region where the backscatter is decreasing with respect to a reference image. So then there are different sources of confusion. One of those is the snow, because wet snow can create a large overestimation of flood extent, because it appears as a really big dark patches, because the wet snow contain there are some water content that absorb the signal and then decrease the backscattering with respect to, for example, dry snowpack, which is quite transparent from at the microwave frequency, and then in that case the backscattering is mainly from the subsurface of the snow. So then during the melting period can create some problem, because the absorption increase, and then we see very low backscattering area. That this could be an important source of can be an important source of error, because also during the melting phase can cause also flood in some area. Then to distinguish the two, it's quite challenging, and there are no simplified model to explain this. In general, to fill this gap, we use time series analysis to investigate to understand when the snow starts to melt. Here is an example. For example, an example over Canada, 2019, a flood event occurred in this area, but we had also the snow melt effect, which is mainly this one, although some flooded areas are present here. So it was quite difficult and challenging to identify and to distinguish this behavior. Here is another example at X band with Cosmos Skymet data. You see here on top of the mountain dark patches, and this is the snow start to melt, while here is water. This was a flood event that occurred in north side of the Italy, and in the image we had flooded area over flat region, but on the Alps we have this effect. In this case, you can remove this effect, maybe considering the EM, because you know that the snow is on top of the higher altitude, but when you appear on flat area, it's more difficult to distinguish. Another effect that can create under detection is the wind effect, which make the surface of water rougher. So in this case, it's difficult to distinguish the water from the land around, because the backscattering is increasing. Then it's not so easy to distinguish the two. And then also, if the terrain around we have higher value of soil moisture, it's very difficult this behavior. In that case, longer wavelength could be used, because are less sensitive to roughness, or also using data with more than one polarization can help to disentangle this problem, because, for example, for cross-polarized channel, the roughness is as a behavior impact less the backscatter, so it's less sensitive to the roughness. Here is an example. For example, for the Myanmar and RADARSAT-2 image, and here we have the HH channel, and here the HV channel. So a co-polarized information and cross-polarized. We see that in the cross-polarized image, the water appears dark, while here it's much brighter. So then using this channel could be useful to detect water, although then this is the cross-polarized channel is more sensitive to smooth surfaces. So then we could have some over detection, because also other smooth surface could look darker. Another important source of error could be rain, where and this is affecting sensor at higher frequency, because we can have attenuation of the signal due to the rain cells, and then, as a matter of fact, we see dark patches over the image we are acquiring. Although it's well known that at microwave the atmosphere is quite transparent, but this is happen when there is really heavy rain. Here is an example. It was really a heavy rain, and in X-band you see this dark area, which is the attenuation due to the rain. Although at C-band it's possible still to see some small effect of this. This was really for the hurricane Irma on 2017 over USA. Here is a comparison with the ground station radar, and you see that these dark patches from Terrasar X fit well with what the ground radar was imaging. The effect of rain can be also not just attenuation, but also create some roughness over the surface, and it's possible to see this effect in this case, where we see here over a river an increase of the backscattering in VV channel, and in VH less. So this is probably due to the effect of the rain over a water body. Then there are other surfaces, like smooth surfaces, that could look like water. This is a tarmac from an airport, which looks quite dark. It can be confused. And also a very dry area, like sand dunes, where there is a lot of absorption depending on the amount of the sand on top of the bedrock. So then here you see that they look quite dark. Here is another case. These are dunes that looks quite dark. And then if you don't take into account this, you can create your map can have some mistakes when you use automatic algorithms. Also, vegetation can create false alarm. Here is an example where we have really dark area, which are caused by absorption of vegetation. So then when you apply a change detection algorithm, so when you compare two images, you have to, in general, use as a reference an image very close in time in order to reduce this effect of vegetation changes, while changes caused by flood are sharper. So now let's move to discuss a bit more how we detect flood over bare soil and then in urban area. And this is are the basic principle of our algorithm that we implemented in the WASD platform. So we use a statistical based approach where we try to parameterize the distribution of water and the distribution of no water in order to detect flood. To parameterize this distribution, or in general, we need a sufficient number of pixels to understand the probability density function of the class of interest. In general, this is easy if looking to the distribution of the image, we see bimodal behavior. So we are able to identify the class that represent water and the class of no water, or class of changes and class of no changes. But this is it just not depend by the extent of flood extent, but also the size of an image. So then it's not it's important to look to the backscattering value, but also the amount of pixel having this backscattering value. So there are approaches to deal with this problem, which that has been called the split-based approach, where you split the image in several tiles and then you look to each one to see if each tile is bimodal to identify these two classes. Of course, as I mentioned, the same event, depending on the sensor you are using, can have a different amount of pixel flooded with respect to the total number of pixels. So then we did develop an approach where we use an hierarchical split-based, because in order to adapt to the different resolution and swath width of the sensor. This is what I was saying before. So here is the image where we have the flood, and then here we have the histogram of the backscattering, and you see that we have two different classes, which is the water here and the rest of the image. So then, if we are able to model these two classes, then we are able to distinguish the two with a classification algorithm. So I was mentioning before, here you have exactly the same flood event, but here is at 150 meters with a bigger image. So this is just a very small part of the flood. It is occupying really a small part of the image, while at higher resolution, TerraSAR-X, this is the entire image, and this is the flood in. The flood is occupying a bigger part of the image, although is still 2% for TerraSAR-X and 0.05% over MVSAT twice watt. So then the need to split the image and look for tiles where the distribution is bimodal is really necessary. So then here is our approach. We use a change detection approach. We pre-process the inputs, so the flood image and the reference image. The reference image is that where the flood was not present. And then we apply an hierarchical split-based approach to select bimodal area where to fit our distribution to classify later on the image. And then the classification procedure is an hybrid methodology that combines region growing and change detection for automatically extract the flood over the entire scene. The pre-processing of the reference to the flood image consists on the co-registration of the two images, calibrate them for geocoding using a DM, and apply the speckle filter to increase the equivalent number of look and to reduce the noise due to the speckle. Of course, when you apply a change detection approach, images have to be from the same orbits. So then it means that they have to be acquired with the same geometry in order to associate all changes due to surface changes and not due to the geometric acquisition characteristic. Then we apply also a logarithmic operator in order to increase the dynamic of low intensity value and then to obtain more symmetrical distribution of the classes that can be modeled with a Gaussian distribution. So the methodology, as I mentioned before, consists of, in the first part, to identify area where we can robustly model our distribution, and then to use this to map flood. So then we look to the histogram of the image. If it's not sufficiently bimodal, we start to split, and we retain the part where is bimodal, and then we continue to split the other part. Here we do on the flood image plus in the image, which is the difference between the reference and the flood, and we take a part where the amount of water is sufficient to identify its distribution. Once we have, so the rule to do this is like that we assume that the distribution of each tile is bimodal, so it's composed from water and water, or changes and no changes. And to assess the bimodality, we use the Ashman-D coefficient. So then once we have the distribution G1, for example, our class of interest, which is water, and G2, which is the distribution of classes around, we use the region growing. So the region growing, we assume that pixels constituting the target class are clustered rather than randomly spread out over the entire image. So we fix the seeds, the region growing with a threshold where we are sure that belong to our classes of interest, and then we apply the region growing, retaining only the pixel which are closer to the seeds we select. At the end, we see that we can put a threshold for stopping the region growing for higher backscattering value, reducing a lot over detection that we could have if we put directly a threshold in this valley between the two distributions without using the region growing. So the methodology, as I mentioned before, that is the first part. To map, we have an input, the flood image, and the image difference between the reference and the flood to extract our bimodal mask, and then using this information, so the fitted distribution, we can apply the region growing at thresholding in an iterative way to get the final flood map. Here is an example, several examples of the result. So then when we apply this approach, so here we have the flood event. We use a 3-meter resolution image from Terra Starex. Here is the bimodal mask, so the area that has been used to extract our probability density function to map the flood extent. And here is the final flood map. So we also validate the algorithm comparing with the optical images with the very high at 20 centimeter resolution. And here we see the agreement between the two map, where we have 90% of overall accuracy. The same has been done using 150 meter envisage watt images. Here are the tiles that have been selected, and here is the resulting flood map. Also in this case, we have validated the results. Also in this case, the accuracy was 90%. So you see that the approach is quite flexible and agile to deal with different kind of frequency, resolution, and size of the entire image. Here is another example, for example, with Sentinel-1 over flood event in Italy in 2014. Here the histogram of reference and the flood image over the entire image. And here are the histogram when we selected only the bimodal tiles. And here the results. So in red, you see the flooded area, and here the automatic map extracted after applying the algorithm that is matching with the red area in the RGB color composition. Here is another event over the Philippines, and you see that there is a flood which is quite small and the image is quite big, and the approach was able to select some tiles to retrieve the probability density function and to map flood all over the entire area. Here is an example, the flood extent in red, the tiles selected, and here the flood that has been mapped. It's not necessary that a tile is selected, because the tiles are selected just to calibrate the probability density function. Then the algorithm is applied over the entire image. Here is the case, and here you can see the detail, so how accurate is the flood extent. Here is an event in Africa, Zambezi, where we have in red the flooded area, the bimodal mask selected, and then the flood extent. So as I mentioned before, now let's move to urban area, where the behavior is quite different. And as I mentioned, that the principle to detect water in urban area is to detect the increase of the backscattering caused by the presence of water. Of course, the environment and the structure are quite complex, so then this increase of the backscattering is not so evident. Then we use also what we call the interferometric coherence, which takes into account also the phase of the SAR signal, because we have to consider that SAR, synthetic aperture radar, is a complex image where we have the intensity, so the backscattering, but also the phase, which is a kind of information regarding the distance between the satellites and the object, and this is much more sensitive to small changes. As I showed before, so we have to focus in the double bands effect, but the double bands which is occurring between the building wall and the surface in front of it, depends also if we look from the top on the ground. It depends also if the facade is orthogonal to the line of sight. If it's orthogonal in the VV polarization, so in the copol data, the backscattering is quite high. But if it's not orthogonal, the backscattering is decreasing in the VV channel. But the advantage, if you have dual pole data, so data that have two polarization, VV and VH, if the double bands in the VV moving from the orthogonal position is decreasing, it increases in the VH channel, because we have when it's not orthogonal, we have multiple bands between buildings that give rise to depolarization of the image of the signal. Then we have an increase in the cross pole channel. So then analysis of the intensity and coherence should be done in both involve polarization to have higher chance to detect changes. So I don't know what happened there. Sorry. Okay. And the coherence, the coherence is a degree of correlation between two images that have been acquired in two different times, and is basically a complex cross correlation between two images. It's calculated using a sliding window, and this tells us how images are changing time. So this is so here is really the comparison between a SAR intensity and the INSAR coherence image that has been computed using two different images acquired at 6 or 12 day distance. It's possible to see that here urban areas are quite bright in the intensity due to the double bands, but there are also some vegetated areas which are quite bright as well. But if we look to the coherence, which is much more sensitive to small changes, urban area remain still quite bright, but all the other areas like bare soil, vegetated area are quite dark. So this is, it's important to know that the coherence, if we want to use the coherence, which is more sensitive to changes, we have to focus really in a stable structure, and in particular to building and urban area, because you see here this is a coherence computed over two images that didn't change, but the changes, small changes in vegetation make decrease the coherence. So the coherence has been used to detect flood with higher resolution data, for example, with sensor like Cosmos Skymed, metric resolution, but also with Sentinel-1 at decametric resolution of 20 meters. The rationale behind is that so the urban area are stable in time, and they have an high value of the backscattering in general, even if they are not flooded. And then we can have a small increase when the flood occurs. And also that the coherence is quite stable if the two images are acquired when the flood is not there. When the flood occurs, we have a decrease of the coherence. In general, with this approach, we use three images, two acquired before the event, where we compute the coherence with two images not affected by flood, and with one image acquired before the event and one during the event, where we should see in this image, coherent image, a decrease due to the presence of the water. As I mentioned already, so the INSAR coherence is affected by temporal decorrelation. So then we have to focus in area where the coherence in general is stable. Then the double bands object, so building in the urban area. And also there is another effect that can make decrease the coherence is the spatial decorrelation. That is due to the distance between the two satellites that acquired the two different images. Although the satellites are from the same orbit, they have an orbital tube that can have a diameter of several meters. And in the case, for example, of Sentinel-1, this is quite small. That make to have a really small perpendicular baseline, so a very small spatial decorrelation. So the algorithm that we use to detect flood in urban area, and then that is implemented in WASD platform, is composed of four main steps. So the identification of buildings, so the double bands, extraction of the pre-event and co-event coherence map using a sliding window, then calculate the difference in coherence over object like double bands, and then thresholding in an automatic way this difference to detect flooded area. Here is an example of how we extract buildings. So the buildings are extracted also from Sentinel-1 at 20-meter resolution using a longer time series of images which are not affected by flood. Here is an example over Houston, where you see in red building extracted using this approach. This was a challenging area because there was a lot of vegetation over this area. Here the Houston test cases over 2017, where we had 2 images acquired before the event to create the coherence map pre-event, and then 1 image during the event that has been used to compute the coherence co-event between the image over October 24th and October 30th. Here is the RGB color composition of the intensity, where we see the changes, degrees of backscattering over Bersoil in red, and here is Houston, where we don't see big changes. And here is the RGB color composition of the coherence, where we see some quite red all around Houston, but this is due to vegetation. It means that the coherence was decreasing also for other reason than the water. And here is Houston, where it's quite bright because majority of the city was not flooded. And then we have some red spot in some part where we see a decrease of the backscattering that we can detect with our approach. So as I mentioned before, here is a detail. So we have in this part from a ground truth, this was a kind of flooded area over within buildings. And here you see that there is a decrease of the coherence. So these red patches are flooded buildings, and here are the results of our algorithm, where in dark blue we see the flooded building, and here the flood over Bersoil. Here is the ground truth from visual inspection of very high resolution optical images, which was matching with our result. Here we have also model result from the FEMA inundation model. And you see that was in agreement with our result. Here is another example over another area, where the intensity we see the flood over Bersoil red, and in urban area we see slight increase of the backscattering if we look just to the intensity, and in the coherence we see really decrease of coherence in this part, although the decrease of coherence is a bit spread around. But our algorithm focused just on buildings, and then in the dark blue you see which were the building flooded due to the for this event. And this is the ground truth from visual inspection, from the crowdsourcing of very high resolution images, and you see the agreement. Here, for example, they didn't put by visual inspection the flood, although this area was completely flooded as resulting from the model here. Here we have another event that was in Somalia, and where the flood lost several days, and then we use 3 different dates to map the evolution of flood in urban area, Balawain, and here is the example. So you see here over the intensity, we see the decrease of the backscattering here in red over Bersoil, but in the city we don't see any change. But if we look to the coherence, we see these red patches. That it means the presence of water in this area, which is quite close also the water over Bersoil in this part, that have been mapped in blue with our algorithm. And then we use an image acquired 12 days after, and you see that the decrease of coherence is increasing, and also the number of blue pixel showing flooded area in this part with the automatic algorithm. And again, days after, where you see that the area, the city, the coherence decrease a lot, and the algorithm is mapping all this area as flooded. You see also that the Bersoil flood is increasing, which is this light blue area around. We have also, here is the last example, we have also the event in Jakarta 2020, where we apply the algorithm. It has been automatically applied to over the entire region. And you see in light blue, bed soil flood. Here is Jakarta in white, which are in white are the buildings not flooded, and in dark blue there are buildings that have been flooded. And here is a detail of it. So you see the in red flood over bed soil in the city area that have been affected to changes in dark blue. Here is the example how the two different polarization of coherence behave, and here also the contribution in different color from the two different polarization, just to show how much is important to use, if possible, more than one polarization to detect water over urban area. So thanks a lot for your time. I hope you enjoy this this talk. Thanks, and it was a pleasure for me to present this. Thanks a lot.
Thank you very much, Marco. I don't know if you have maybe time for some urgent questions to Marco. I don't know, we have quite a high number of participants, but is there anyone who has already a question at this stage to what Marco has presented? Otherwise, I will start sharing my screen to move to the second part of the presentation. Can you see my screen?
Yes.
Okay, great. So Marco has shown us now the theoretical background of the algorithm that we are using to map floods over large scale using radar imagery. The topic of this second presentation is to show you how we move from such a science-based retrieval algorithm, or rather a sequence of science-based retrieval algorithms, to an operational service. And I give you the example of the eDrift services that are now currently implemented on WASD. So as I said in the beginning, we are from the Luxembourg Institute of Science and Technology, and that's a research and technology organization. So we one of the objectives of our of the work we do is to move such science-based algorithms towards operations. So this is something that is really one of the main thematics of our research group. And I think the eDrift project that I'm going to present you now briefly is a very nice example of how we start from a scientifically validated algorithm to build an operational service that directly benefits a large number of applications. So in 2018, the European Space Agency and the World Bank, they have teamed up to enhance the use of satellite Earth observation-based analytics to support evidence-based decision-making for the disaster risk financing industry. So that project that we started at that time was called eDrift. It was done in collaboration with the CIMA Research Foundation that had the lead of that project, and the private company Fade Out, that had developed an exploitation platform that I'm also going to present you in a bit more detail on the next slides. So what were the main objectives of eDrift? As I said before, the main goal was to develop applications that take advantage of the large amounts of satellite Earth observation data that is now readily available from the European Space Agency and other international agencies. And the applications that we were expected to develop should support decision-making in the different phases of flood risk management. So first of all, the goal was to better understand disaster risk in all its dimensions, so including vulnerability, exposure of persons and assets, the characteristics of hazards. So this is, of course, based on the exploitation of large collections of satellite data acquired over long periods. And then the second objective is to contribute to enhanced disaster preparedness. So not only the goal is to better characterize the risk and understand what are the areas that are affected by flood risk, but also the goal is to use the data to better forecast events and to allow to take action in anticipation of flood events. And then the third objective is to strengthen the emergency response. So to make use of recently acquired satellite data to monitor the event and to pass on important information to the emergency responders. And for this project, we were focusing on the flood-prone areas in 3 countries in Southeast Asia. These were Myanmar, Laos, and Cambodia. So we started with the algorithm that Marco has presented before, and it quickly turned out that it's quite a challenge to use such an algorithm in an operational framework and to use it systematically, in a fully automated way. So, but that was the goal that we were having at the beginning of that project. So we wanted to enable a systematic and automatic satellite Earth observation-based monitoring of water bodies at large scale in near real time. And to do that, 2 main challenges had to be overcome. The first one was that we had to continue developing the retrieval algorithm that Marco showed you before. So it has to be efficient. Of course, the time between the acquisition of the satellite data and the distribution of the final maps has to be minimized or shortened. The algorithm and the workflow have to be perfectly robust, since it will be used in an operational context. And also we need to achieve high classification accuracies in diverse landscapes and different acquisition conditions. Marco has presented you already some of the, let's say, problematic areas like very dry land or urban areas. So we had to make sure that the algorithm we develop is able also to recognize the floods in such challenging environments. Then a second challenge, which is more an IT challenge, is that we need also to make sure that we get fast access to the imagery, and that we have also access to high-performance computational resources in order to respond to the needs of the emergency responders and the disaster risk financing sector. And so to achieve these goals, we brought together 2 technologies. So on one hand side, we used an EO-based mapping approach that we call Hazard, which we have developed and then intensively tested over different areas of interest in Southeast Asia. And the second piece of technology is the WASDI exploitation platform that provides fast access to satellite imagery and the possibility to process these large collections of satellite data in an efficient way. So the goal was to implement the Hazard software on the WASDI exploitation platform. So what is the advantage of an exploitation platform like WASDI for a group like ours? So as I said before, we need to have fast access to multi-source Earth observation data collections in a timely manner. So of course, when you develop the algorithms and your goal is to publish your work in scientific papers, the efficiency of the workflow is of secondary importance. But in an operational context, of course, it's rather obvious that the time difference between the acquisition and the distribution of the final map is of paramount importance. So WASDI helps us to have this fast access to different collections of Earth observation data shortly after the acquisition. Then it's not only a matter of having fast access to the imagery, but it's also necessary to have access to cloud computing infrastructures that allow you to process the images in an efficient way, and not only the images, but also to combine the satellite images with other data products that help you to contextualize the maps that you are producing. Then the third objective is to frequently update the flood extent maps as the event unfolds. So it's one application to do a mapping of a flood extent on demand, so whenever a major event occurs. But the goal is to fully automatize the procedure so that an end user or an operator doesn't need to trigger a processing when an event happens, but the system does this automatically and also continues to monitor the event in a fully automatic way. Then, by combining the satellite imagery with other data that is available on the VASDI platform, we can also immediately detect the impacted infrastructure and also estimate the number of persons affected. These are, of course, the two parameters that are of highest importance for the emergency responders, but also the disaster risk financing industry. And finally, we also need to have access to the computational resources that allow the processing of large data archives. So not just pairs of images or single images, but entire collections of satellite data that were acquired over long periods to assess flood hazard and risk at large scale, and also to detect any changes in this flood hazard and risk over time. So our algorithm that was introduced by Marco beforehand is based on change detection. So as he has shown, normally the input data is a pair of satellite images. So one that was acquired during the event and one that was acquired before the event. To reduce any false alarms, it is of course necessary to make sure that the changes that we detect are related to the appearance of flood water and not other effects like, for example, vegetation that is growing or an area that was covered by wet snow. So it's important to automatically select the most adequate reference image from the collection that can be found. And this reference image should have been acquired close in time to the actual event. And while it is relatively straightforward to find an adequate reference image for flood events that only last a few days, the situation becomes much more problematic when you have flood events that last several days or even weeks and months, as we could see in some regions in Southeast Asia. So in that case, it's rather difficult to find immediately the most appropriate reference image. And the question is, what is, in that sense, really a reference image? So this were the two particular challenges that we were facing when we started this project, and we were aiming at developing a fully operational flood monitoring system for the 3 countries in Southeast Asia that I mentioned before. So our algorithm was developed and adapted for this particular context of monsoon-related floodings that last several weeks and months, in such a way that, first of all, to select the reference image, we automatically select an image that is obtained from the same orbital track and that was acquired close in time to the flood image. So this helps us that in the way that the changes that we detect on that pair of images can be related to the appearance or disappearance of flood water between the 2 images, and other changes, they are less impactful. In fact, to also take into account the fact that these monsoon-related floodings last several days or week, and the difficulty to find a reference image in that case, we rather set up a continuous monitoring chain that detects all kinds of positive and negative changes that can be related to the appearance and disappearance or recedence of floodwater between 2 image acquisitions. And I'm going to show you afterwards how that works. So rather than selecting a pair of images and detecting the changes, we continuously monitor all satellite images that are acquired from the same orbital track and detect positive and negative changes that we can attribute to the appearance and disappearance of floodwater. So the ideal instrument to set up such an automatic and systematic flood monitoring system is the constellation of two Sentinel-1 synthetic aperture radar satellites that are currently operated by the European space agencies. So these two satellites, they provide a systematic coverage. And what is very important is that the acquisitions are done in a systematic way. So there's no need to task the satellites to take images over a certain area. Rather, it's possible to process all incoming images from Sentinel-1 without having to interact with the operators of the satellite. And the data is, of course, available freely. So that was our main data stream that we took advantage of. So we adapted our algorithm in such a way that all Sentinel-1 images acquired over the regions of interest were processed with the algorithm that we had developed. Then from interactions that we had with different user organizations, it became apparent that it's not sufficient to just monitor the extent of flood water, but there are some other pieces of information that are needed to contextualize the observations that we obtained from the satellites. So other than the flood extent, we developed a new product that we call an exclusion mask, and that I will explain you a bit more in detail later on. So this product should highlight all those areas where no reliable classification can be obtained, so that an end user knows that there are some areas where no classification could be achieved, and thus the status of the flooding in that area is unknown. Then it's also important, and in particular in the regions in Southeast Asia that we were targeting, to have access to additional data that inform us on the permanent and seasonal water bodies. Especially the seasonal water bodies is a very important piece of information, because it helps you to distinguish the, let's call it, extraordinary flood water from areas that are inundated on a regular basis every year in a given period. And by processing the large collections of satellite data, we can also derive a product that informs on the flood frequency in the different regions. So we can aggregate the flood maps obtained over many years into a single product that informs on the likelihood of having a flood in different regions of the area of interest. So as I said, Sentinel-1 and the two satellites that currently constitute the Sentinel-1 constellation are the ideal instruments to set up such a systematic service. So here on the screen you see a map that was obtained from our colleagues from the Technical University in Vienna. It gives you the average revisit time achieved by the two Sentinel-1 satellites A and B in interferometric wide swath mode, based on acquisitions obtained in 2017. So over Europe, you have the highest, and especially in the higher latitudes, you have the highest frequency of acquisitions. So on average, every 2 to 4 days, a 5 meter to 20 meter spatial resolution is obtained in that area. But as you can see on this map, also in Southeast Asia, the frequency of measurements are quite high and vary between 2 to 8 days. So on average, every 2 to 8 days, you have an image over any given area in that part of the world. And that was already explained by Marco. There are also some other features of Sentinel-1 that make it a perfect instrument, in particular for applying SAR interferometry, which is important to detect water in urban areas, as I will show in a few minutes. So our algorithm has been implemented in the way you see here on the screen. So that's the workflow that is currently available on the exploitation platform WASD. So we use as inputs to our chain the most recently acquired Sentinel-1 pre-processed scene. It selects an adequate reference Sentinel-1 scene that was acquired from the same orbit and close in time. Then we use as static products the exclusion layer that I briefly introduced beforehand, so that we know what are the areas where no classification can be achieved. We use also the different reference water layers, so the permanent water body, but also a seasonal water body layer. And we need also the flood extent map that was generated at the previous time step, because that is the map that our workflow is then updating using the most recently acquired satellite image. We also use a database of historic parameters that we can make use of to detect any anomalies in the parameterization of the distribution functions. Then the two outputs are the observed flood extent, and by combining the flood extent with the permanent water bodies, we get also an observed water extent product. So the algorithm can be summarized in 7 steps. We start by mosaicing all the latest SAR acquisitions over the entire area of interest. So all images that were acquired on a given day are put together in a single data set through a mosaicing procedure. The next step is then to tile this mosaicked image. Each tile has a size of 100 by 100 kilometers. This is done mostly to render the parameterization of the distribution functions more robust. So we have a specific set of calibrated parameters for every single tile. Then once we have generated these tiles, we apply the flood mapping algorithm, which consists in first applying the hierarchical split-based approach that Marco showed you beforehand. So we cut every tile into sub-images to detect those areas that enable a robust parameterization of the algorithm. And we do that not only for the most recently acquired Sentinel-1 image, but also the one that was acquired from the same orbital track before, so that we can detect any significant changes that happened between the two acquisitions. Then when we use this difference image composed of the most recently acquired image and the one obtained previously, we detect all the areas where the water has appeared. And by inverting the role, so using first the image from that was acquired before and the most recent image later on, we repeat the same step to also detect all those areas where water may have receded since the last acquisition. Then the result of these steps 4 and 5 is that we have detected all the areas where water appeared and disappeared, and we make use of these two positive and negative changes to update the flood map that was obtained at the previous time step. So we remove all the pixels where the water has receded, and we add to the classification all the pixels where water has appeared since the last acquisition. And in the end, we mosaic the flood maps from each tile into a single to create a single product. Just to illustrate how this works, so typically here you see the Sentinel-1 images acquired on a given day over an area in Myanmar. So we have first of all the Sentinel-1 images from that day that are all mosaicked, and we do the same with the images acquired from the same orbital track previously. And then the tiling is performed as you see here on the right-hand side, so to cut this mosaicked image into sub-images corresponding to tiles of 100 by 100 kilometer. And here I want again to illustrate this how this algorithm works when we don't apply it just on a single pair of images, but we systematically process sequences of images acquired over time. So here you see the Sentinel-1 images showing a flood situation in Myanmar. By using the RGB composite, or computing the RGB composite, you see in red the areas where the backscatter has decreased between the two acquisitions, and in blue the areas where the backscatter has increased. So our algorithm uses this pair of images then to detect the areas that that have not changed since between the two acquisitions. So these are the areas in black and white. And in red, you see the areas where we consider that the floodwater has increased, and in blue, the areas where the floodwater has receded. Then, as I mentioned before, we take the flood map that was computed at the previous time step, and we add and remove the pixels that have been identified as positive and negative changes with our algorithm. And this we do it over time. So systematically, when a new image is acquired, we update the flood map that was acquired at the previous time step using this map of positive and negative changes. So I would like to present you now briefly the main products and also some of the value-adding services that are available on the WASDI exploitation platform and that are now accessible to end users. So here on the right-hand side on the top, you see an example of a flood situation in an area of Myanmar. And this illustrates the three main products of our service. So you see on the one hand side in dark blue, the flood water. And as to contextualize this information, we also indicate in light blue the permanent or seasonal water bodies, and in orange the excluded areas. So to compute the reference water mask indicated in light blue, we take satellite images that were acquired over a period of 2 years, and we compute a median backscatter image from that sample of images, and run our algorithm on that product to detect all the water bodies that are systematically visible on that area of land. And we do the same also for every single month. So for every month of the year, we compute a median image composed of all the images that were acquired over a period of 2 years to also see how the seasonal water changes over time. And then the third product, which is indicated here in orange, represent the excluded areas. So for this, we combine effects of no sensitivity, of water lookalikes, of radar shadows, and topographic distortion. So this informs the end user on areas where no classification can be performed. And these products, the Sentinel-1 reference water mask and also the exclusion mask, have also been pre-computed for Indonesia and are available on the WASDI platform. To add value to the product that we obtain, it's possible not only to look at the current flood situation, but it's possible also to run the algorithm over the entire archive of Sentinel-1 images acquired since 2015 and the launch of that mission. So we can, on the one hand side, generate what we call a flood record or a flood archive. So we can go back in time and see how the flood situation looked like on any given date in the last 6 years when the Sentinel-1 image was acquired. And we can combine all the maps into a single product, which we call a flood frequency map, which you see here on the screen. So it shows you how frequently different parts of the area have been flooded in that 6-year product. And we can also compute a product which we call a maximum flood extent that, as the name suggests, indicates the maximum extent of flooding in that 6-year period. And this archive, of course, is evolving. So whenever new images become available, they are put into the archive, and the flood frequency and maximum flood extent map can be updated. Then there are other products that are important to the end users and for which we need external data sets to generate those products. So from the disaster risk financing industry, for example, we learned that the most important parameter they were looking at was the estimated number of people that are affected by flooded areas. And also they wanted to know what kind of land use classes are affected by the flood. So to estimate the number of persons affected by the floods, we used we used the global human settlement layer, which is a population density product. So when you overlay then the flood extent map obtained through our workflow with that external product, you can produce maps that inform on the number of persons affected by the event. And you can do the same with a land use product or land cover product, for example, the Copernicus Global Land Cover Service, or the Copernicus Pan-European High Resolution Layers and the OpenStreetMap, to provide an update on affected land covers, as you can see here with the example on the right-hand side. And also in Myanmar, we tested an approach that consists in combining the simulations of a hydrodynamic model with the observations obtained from satellite. So this has different advantages. The first one is that we can, in that way, refine our water extent map. For example, in areas that were excluded from the classification, so like densely vegetated areas, for example, or some of the urban areas, you can use the hydrodynamic model to refine the water extent map that was obtained from the satellite. It's also possible to use this combination of the simulations with the observations to not only assess the extent of the flood, but also to estimate water depths, and also to quickly estimate the return periods of ongoing floods. So for this, we use a catalog of pre-calculated simulations that represent the flooded areas according to different return periods, and we find the image that has the best match with the recent observations. So we can then not only estimate the extent of the flooding, but also immediately attribute a return period to the extent that was observed by the satellite. So we have currently 3 applications that are based on this workflow available on the VASDI exploitation platform. In the next session, after the short break, we will present you in more detail how these applications can be used. I just want to give you a very quick overview of the 3 applications that are currently available. So the default application, and I would say the application that we developed in the first place, was what we call an on-demand flood mapping. So the on-demand flood mapping means that any user can manually select an image he wants to process. So let's call it the flood image. And he selects an appropriate reference image from the ESA data collection, and then launches the process to have an on-demand generated flood map. So you see here an example. So a user takes an image from the archive. He selects the reference image that is acquired from the same orbital track close in time, and then you can run the process to generate a flood extent map and download it to your work environment. Then the let's say the systematic variant of this application minimizes the interaction with the end users. So here in this case, the end user only needs to delineate his area of interest and define the period of interest. And then the system systematically processes all the images that are acquired over that area and in this time frame that was defined by the users. And in the end, you can download the different flood extent maps that were generated, and also the final products like a flood frequency map that can be derived from the individual maps. So this will be also demonstrated in the next session by my colleagues Paolo and Ramona. So for Indonesia, we did already this exercise. So we processed the entire archive of Sentinel-1 images acquired over the island of Java between 2015 and 2021. And this data can be accessed through the VASDI platform. Then our latest application that we have added is an on-demand mapping of urban floods. So that's based on the algorithm that Marco introduced in the previous talk. So you see the effect of this new application by looking at here the screenshot from a VASDI computation. So you see in dark blue the flood water that is acquired with the, let's say, the standard procedure that I explained to you beforehand. But by adding this urban flood mapping module, we can also identify all the urban areas in the same region, and then make use of any detected drop in coherence to find also the water inside the build-up areas, as you can see here on top, for an example of the flood that occurred in Japan in 2019. Here's another example, or zoom in rather, where you see the city that was all the buildings can be detected with the algorithm, and then we run our algorithm to find the areas where the flood water could be observed. And another example here, also from Japan, again in dark blue, the flood extent obtained mostly over bare soils and vegetated areas, and then using this new module, we can then also detect the floods in the urban areas. And I would like to conclude this introduction to hazard on VASDI by informing you that you are, of course, welcome to start testing the different hazard applications that Paolo and Ramona will show you in the next talk. For this, we would like to kindly ask you to send an email to the address that is indicated here on the screen, so that we can create an account for you, and so you can start using the different hazard applications based on the information that you will receive in the next talk. And that's it for the moment. I don't know if you have any immediate questions before the break. Please do not hesitate to do so. I just want to show you, if I manage to do that, the schedule of the day or the agenda. I think we were now supposed to make a short break of about 10 minutes, and then we would move on with the live demo and the tutorial. And it will be Paolo Campanella and Ramona Pelic who will present that part of the session.
Okay, thank you, Patrick Madgen and Marco Pancini, for such interesting material. So, Bapak dan Ibu, tadi kita sudah mendengarkan penjelasan mengenai bagaimana penggunaan microwave remote sensing data dalam pemetaan banjir. Kita akan lihat selama 10 menit. Kita akan kembali bergabung pada pukul 14.55 untuk mendapatkan penjelasan yang lebih menarik lagi mengenai bagaimana mendemonstrasikan hazard apps di WASDI platform. Sebelumnya saya akan menanyakan kembali, Patrick, you said that you require some email from the participant to be registered an account.
Yes, that is correct. I mean, Paolo Campanella, who is running the VASDI platform and is in charge of it, he will give more information on this in the next talk. There are some reasons why we could not create now an account immediately for every user. So we want to limit the number of users that will be start processing images on the platform. So we would like to invite those that are interested in testing the applications to write us before, and so that we can also have an overview of how many people will be using the application at a given time and organize this in an efficient way.
Okay, so how many email do you think?
This, I don't know. We will have to see. Everybody is invited to use the platform. Please send us an email to the address that I had indicated on the slide, and then we will create these accounts and maybe organize, distribute this over time so that we avoid having too much traffic on the platform at a given time. But again, it's Paolo Campanella who is more competent than me to explain you exactly how that can, works best.
Do you mind if we can have your slide with the email again? So maybe the participant can start to send you an email.
Yes, of course. I mean, in any case, all the PowerPoint presentations are available on the Google Drive. So, and they will be also available on an e-learning platform that we have set up with our colleagues from the GMA Research Foundation. They can be found there. But of course, we will repeat this email address also in the next talks, just to be sure that people have this information.
Okay. Thank you then, Patrick. Bapak Ibu sekalian, baiklah kita akan rehat sejenak. Tadi disampaikan oleh Patrick bahwa nanti bagi Bapak Ibu yang tertarik untuk bisa mendemokan Hasad Apps di WASDI, bisa mengirimkan alamat emailnya. Baik, terima kasih. Kita akan rehat selama 10 menit.
workshop kendaraan mobil ya.
Ya. Baiklah, Bapak dan Ibu serta hadirin sekalian, selamat bergabung kami ucapkan kembali kepada Bapak dan Ibu serta rekan-rekan yang saat ini telah terkoneksi melalui jaringan Zoom meeting dan menyaksikan kegiatan hari ini melalui kanal YouTube channel PUSFATJA LAPAN. Sekali lagi kami informasikan bahwa acara ini disiarkan secara bilingual dan bagi Bapak Ibu yang mengikuti melalui Zoom bisa mengaktifkan fasilitas interpreter untuk memilih bahasa yang akan digunakan dengan memilih tombol di bagian bawah layar Bapak dan Ibu. Marilah kita lanjutkan kembali sesi pembelajaran, and in this time we would like to invite you again, our colleagues from LESD and WASD, to continue our session. I offered this time and screen to you. We would like to also remind you again to have that we'll have a first break for 10 minutes at the second break for 10 minutes at 4 p.m. Time is yours.
So, can you hear me?
Yes.
Okay, so good afternoon to everyone. First of all, I am Paolo Campanella. I am one of the manager of WASD and also, let me say, probably the technical leader. First of all, I would like to thank you very much for joining us in this event, and also I would like to say that I'm excited also to see later the experience from your country. Let's say in this first 20 minutes, I'm going to give you a general introduction, general view of the WASD features. So let me share my screen. I will start with only one slide, just one, because we need to introduce the concept of WASD. In this slide, I hope you see it. We highlight the 4 different actors, possible actors that can interact with WASD. On the right, we have the what we call the end users that can interact with WASD with the web interface we are going to see in a few minutes. The end user, in our opinion, in the idea, in the dictionary, in the glossary of WASD, the end user for us is someone that is not an EO expert. It, let me say, doesn't neither care so much about details of algorithms and so on, just need the result. So just need the flat map, just need the binary area map, the result. You know, it can be a decision maker, it can be a position like this. Instead, on the bottom, we are the real feeders of WASD. The real feeders of WASD are the EO developer. So, for example, Marco Chini that talked this morning, Ramona that will follow me, and I'm more than sure that many are available in your country with all the expertise that you have. I'm talking about the people instead that is expert in remote sensing, so is able to extract this information from the data, from satellite data, and so create new applications. In WASD, they can use what we call the WASD libraries, because WASD is designed to let them, I would say in the most easy possible way, scale their processor from their computer to the cloud. Then we have the EO expert, the other something in the middle. It maybe is a Earth observation expert, but not a developer, and maybe can use Snap workflows, can use manual search of images, and again, this can interact with WASD using the user interface. Last but not least, all that we are going to see now live, all that you will see from the user interface is also callable from a machine-to-machine interface. This is very important because it means that WASD can be interconnected to many, all the possible third-party systems. So, given this introduction, okay, let me start with the introduction instead of WASD user interface. I just logged in here, okay, and when you log, you land in what we call the space market. On the top blue bar, you have what we call the different sections of WASD, and we are going to take a look to all these sections. Let me say that in these first 20 minutes, I will give you an idea of an end user experience, okay? Then we will have again a quarter of hour at the end where we will take a look instead to more EU expert features. So what we are trying to do is to make the life most easy as possible. In the marketplace, in the space market, you can filter different applications for different auxiliary categories, okay? You can search, you can order, and whatever. And all this application of WASD share the same schema. This means that I'm going to click start an application that is not about flood, just to give you an idea of how it works. You can select one application. For example, this is an image creator from Sentinel-2. When you click on application, you have the details. So you can take a look to the review that other users made to this application. Some statistics that are quite important. How many times this application has been executed, no? The medium execution time and the success rate of the application, and also information about the publisher of the application. When you decide that you like this application, you want to see it, just open it. Now, this is again the real user interface of the application. All the WASD applications share again this schema. From the bottom here, we have the last three tabs, we call it section, okay, that are shared by all the application. The last one is more for technical. It has JSON representation of the parameters, not important in this moment. Here we have our history, so how many times we run this application, okay, and you can come back to your old result. Here you have the help of the application, so you can look at the details of what you are doing. For example, this is a very simple image creator. We can decide to extract a RGB or a false color, SWIR, agriculture, geology. We can have different combinations that we can extract. On the other sections instead are obviously specific of each application, okay? More or less, they all share the same schema, let me say, okay? And the biggest part of the automatic applications are organized where, for example, you just select a bounding box, okay? You select, in this case, the type of image to generate. Let's make a false color. I mean, in this moment, I'm not looking at all at the result, just to show you which is the user experience working with WASD. And you click run, stop. The application now is starting. Obviously, this is a very simple and quick application. Should finish in a few minutes, or not finish. I don't know exactly what I'm doing. I'm live and just showing again the functionalities. When we click at run, WASD moved us to the editor part. If you see here in the blue bar, now this is a little bit highlighted. I don't know if it can be seen very well in the sharing screen, but it is. So now we are in the editor. In the editor, you have the processing bar of WASD, okay, where we can see what's happened. We started our application, and in this case, for example, our application started to fetch 4 different Sentinel-2 images that are in the area that we selected. We are searching obviously for the most recent available images, and if I'm not wrong, for example, this image is last night, so I mean very recent. Some modern instead a little bit less. Obviously, forget again about the specific workflow of this application. This is the concept. Here you have your processing bar. Once you start fetching the images for you, okay, and you can follow the execution, okay, of your application. For example, clicking here in the logs button, where you can see the live logs of your application. Let's imagine, obviously, that if you are a NEO expert, in the same way, here is your software that writes this log, no? So you expert decide, the application creator decide what to write here, and the user can read, but also the developer. Let this application work a little bit, okay, and take a look to some other sections. What I just creating my application is called a workspace. We call it workspace in Swazi. Can you call it project? You can call it workspace. It is the place where you are running your application and making your elaboration. So each user can have as many workspaces as he wants. And this is the workspace section of WASD. In this workspace section, obviously, you can come back to your old workspaces, okay? So when you click, you can have some information. Later, I will show some of these workspaces because something that will be interesting. And also because you have to know, I will show you that all the workspaces of WASD can be shared. So you can decide that if you keep it private for you or decide other user that can have access to your workspace. For example, from here, you can see that I have my own workspaces. This is the one that we just created and is working. While instead, here I have many workspaces shared with me by different users. In WASI, we also have a plan section, okay? In this plan section, you can have, let me say, an idea of the future acquisitions. This is more usual, probably most used for satellite, like the Italian Cosmos Climate, where you can, let me say, task the satellite, obviously, but can give you also an idea of the Sentinel. So you just select your area, again, select the mission you are interested, and you can see in the future, okay, where the possibility to acquire images. Okay, this is called Cosmos Climate. I don't know if I won't find. Okay, it looks like Sentinel doesn't pass in this area. Okay, here is one Sentinel, for example. Okay, we pass. Oh, this should be today, so later. Okay, then what about instead the search section? Okay. Again, this is a interface that probably you have seen in many platforms online. We know that there is nothing so much different here. What is different in WASD, in our opinion, is that WASD as a platform is multi-cloud and multi-data provider. This means that your application runs in different cloud environment. For example, we have in this moment active, we call it computing nodes, and we have computing nodes active in CreoDias, in Onda Dias, in EODC, and also in Advise.io, that is a cloud provider, Luxembourg, for example. This is important in our opinion because it makes the platform very resilient, okay? Because it happened, not so often, but happens, that a cloud environment can have a problem. For WASD, this is not such a problem because it can switch to another cloud. It's the same for the data provider, okay? So if I just select an area around the island of Jakarta, and let me say here, you can see all the mission that you can query with WASD, okay? If I click search, the results are not only from one single data provider, WASDI had not its own catalog, sorry. It is just making the query to all the different data providers. So in this moment, we are connected with Onda Dias, Sentinel Hub, I mean the ESA Sentinel Hub, LSA Data Center, Luxembourg Space Agency Data Center, the Sublu Dias, EODC from Austria, Creo Dias. Also, there are different data providers for different data. For example, VIRS is the NASA mission, and in WASDI, for example, we can import the one-day composite flat map, daily flat map. It is a coarse resolution, no? So not fine, obviously, but every day you have this map from NASA that maybe you could be interested to take a look. There is also an application. So the concept is that the search section is multi-mission and multi-data provider. So we are coming back to our editor, okay? In the meanwhile, our application finished. You can again come back here in the processing bar, no? And take a look to what's happened. Okay, you see, all went well. Wow, because this is a live demo, and every time something can happen. You can download the history, okay? Once you have your image, your result, obviously you can also download your result, but also view it directly online, okay? The first time you look an image, you have again to wait some seconds. What I would like to stress, at least to make you notice, is that we just run again a very simple application, a false color image, you know? So it's not, this is our live result, okay? Obviously there were clouds. I didn't, you can select also in an advanced option the maximum amount of cloud that you allow, no? Now I was relaxed to try to have a result. What I was saying is that here, this very quick demo is the concept, because, okay, this application is very easy, but we took in total 5 minutes, and if you take a look at what we did in these 5 minutes, we were able to access and process 4 Sentinel-2 images for more or less a couple of gigabytes, little bit more than a couple of gigabytes, all done directly in the cloud and in 5 minutes. So we think that the application can help end users without expertise, because the same workflow can be done for this false color image, but also for the flood map. Also, and Ramona will show you this, and also for the urban flood map. Obviously, the difference is that when you run a full flood map, it takes maybe 1 hour, 1 hour and a half. A urban flood can take up to 4 hours, okay? Because are a very complex application that handles a huge number of images. But the experience is the same. Just make a bounding box and click run. Select the data and click run. From the expert's point of view, what we think that can be interesting, we will talk later. Let's imagine that you can develop on your computer in your own environment using your own language. When you are ready, you can just drag and drop the application in WASDI, and you will be able to test your code directly to the cloud. This means that you can scale up without the need to stress the resources of your computer. What I want to show you, for example, now, frankly speaking, while Patrick was talking, I made a little test to see and to show that, for example, here we are ingesting Sentinel-5P images, okay? And this is one image that I liked, I mean, because I saw here, this is NO2, so it's pollution, air pollution, okay? And I saw here this red spot, and if you take a look, it's clearly around Singapore. So, I mean, probably you know very well all the possibilities that you have using at observation data This is just again a sample. Sentinel-IP data is available, okay, also in WASI. This is just to again tell you that this is a general purpose platform to create, deploy, and run application. Obviously, the application that now Ramona is going to show you in details are probably the most, let me say, one of the most important applications that we have that are more tested and that are used by many users all around the world. And so, I mean, again, as Patrick said, I invite you to ask us if you want to test the application. And at the end of this session, I will give you again the registration mail to ask an account to us. Okay. Okay. Just I'm adding now a new image just to fill the last seconds, and I think that I can leave the floor to Ramona that will show you again in details the flood-related applications. Thank you very much for your presentation until now.
Thanks, Paolo. I think we need to improvise a bit because Ramona just informed me that she was in a building where there has been a fire alarm now, and she was asked to evacuate the building.
Okay. I love improvisation. I'm Italian.
So I don't. She luckily her flat is very close to the research institute, so she's going back home, and she will try to connect in a few minutes to do the demo of the different applications. But Paolo, if that's fine with you, maybe we can move to the third or the fourth point of the agenda, so that you can show what data is already available from Indonesia in the workspaces on WASI, or to show how the EO experts can deploy their codes on WASI. I don't know what you would prefer. I hope that Ramona will be available in 5 minutes from now, but I'm
sure.
News from
No problem.
Sorry for that.
But it's not your fault, neither the fault of Ramona. Safety first, so it's good that Ramona, hope that everything is okay with the fire. And sure, no problem at all. So, hi again, I'm Paolo Campanella. No, I'm joking. So I was telling you before that in WASI you have the possibility to share workspaces. For example, this workspace that I'm playing, you know, nothing serious. How to do this? You can just click here, share, and you put email of a user of WASI. In this moment, I'm sharing with Ramona that will see this workspace when will arrive. And you just click share, okay? This is all that you have to do. Once our space is shared, other user can access it. Why I say this? Because in different workspaces, we have or calculated or uploaded the data that may be of your interest, at least maybe. And obviously, again, if you are interested, just ask, okay? We will register you in WASI and give you, share with you these workspaces. So the first one that I want to show you is the flood frequency map. Has been done in this area, as you see, okay? So when you open, you just have in the workspace 2 maps, okay? The flood and the data. What does it mean? This is the so-called flood frequency map that show you pixel per pixel how many times that pixel has been flooded in the in our archive. What is our archive? Our archive run the hazard bare soil flood detection for all the history of the Sentinel-1 images available. So more or less starting for 2015. This is, I mean, I would really appreciate your feedback if someone of you will be interested and will take a look to this file. I don't remember if I did it before. I don't know how big is this file. Remember then from WASD, then you just click download, okay, and you take the file. Okay, now the file is on my computer and you can take it in QGIS or your tool, whatever you want. Maybe it's worth to say that in this, in this workspace, there is also this second image. Because thinking on the concept of a flood frequency map, if you spend 2 minutes and you can imagine that not all the pixels has been observed the same number of times. This is because the Sentinel coverage of the country is not uniform, obviously. Sentinel images doesn't pass every day. Different orbit can pass in different days, obviously. And different part can have different updates, or can be also sometimes a little problem from ESA, from the satellite. So this means that we counted each pixel how many times has been flooded, but you also have the auxiliary data that tell you that pixel how many times has been observed. Okay, because obviously make a poor frequency. Okay, frankly speaking, is not correct, because the concept of frequency should have on the same number of observation. But you have both information, and so you can reconstruct what the processor did. The second workspace that we will share with you is, let me find it, ADB. I have too many workspaces, so I can show you this interesting feature to filter workspaces on the top. Okay. No. Okay, this is this one called the Indonesia exclusion map, and in this workspace we have uploaded the information that Patrick was referring before. So we have the combined exclusion layer. Remember that I am an IT, so ask better to my list colleagues, but no, this should be, you discussed it, you should know what is the exclusion layer, and all the monthly reference water maps. Okay, so you can see from here that this is January, February, and so on, and at the end this is really the permanent water map. Okay, that you can download and use and or integrate directly in your algorithm processor that you can run in WASD. Then, last but not least, there is a third workspace that can be shared with you. That again, in my opinion, can be very interesting. My opinion, but will need some time to let me say, analyze it, okay? Because this is the full flood archive. It is called Indonesia Archive New. You see here that we have 2,000 products, because this is the source, okay, that has been used to compute the flood frequency map. So you can see daily flood map. Daily, obviously, when the satellite was available, okay, and each map can cover maybe not all the area, obviously, no, but a sub area. Okay, usually, typically a sub area. But again, here you have all the flood map. I hope you can see from the monitor, starting from 2015. This should arrive at the end of 2021, if I'm not wrong. No, 2020, sorry. And okay, you have it here. Okay, no, it was done until September of 2020. Then, obviously, if needed, we can also add the last months. Okay. So mainly, I would say that these are the workspaces. Also, one that, but I suppose that many of you, some of you at least, already have seen it. But if you're interested, we can also share. This goes a little bit more in the direction of what Ramona will show you, but is the other workspaces in your country where we had the flood maps of the event, the very bad event that has been occurred in February. And in these workspaces, we just collected all the result of the different flood map that we made in collaboration with your colleagues in that days. So this is the base soil map of the event. Okay, so the full the classic hazard. What was nice to see, nice from only obviously from a technical point of view, because nothing is nice in an event like this, but to see that where the limitation of the bare soil flood that doesn't see nothing in the city, while at the time it was a standing new urban flood, instead was able to detect flooded areas inside the city. Then with these hazard layers, okay, we were able also, thanks to the population layer, if I'm not wrong, this came from the DLR, we were able also to compute affected people. Okay, so this layer show on top of the water the estimated amount of people affected, and obviously from the application you can also reconstruct the numbers. Patrick, I don't know if because I'm talking and looking at my screen, so I don't know if Ramona was able to join us again.
First of all, thanks a lot, Paolo. I see that Ramona is now again connected.
Yes, I'm here. Hello.
Perfect. Good to see you.
Are you safe? Yes.
Yes.
Okay. That's important. Okay. So I stop share for now and I leave the floor to you, Ramona. Are you ready? Okay. Can you take it?
Yes. Yes. Okay, so hello everybody. My name is Ramona Pelic. I'm also working together with Marco Chini and Patrick Mattigan at the Luxembourg Institute of Science and Technology. And today I will present you some of the services that we implemented on the VASDI platform that Paolo was just showing to you. Just let me share the screen. Can you please confirm that you are seeing my screen?
Yes, Ramona, I can see.
Okay. Okay, so here we are in the VASDI platform, and I will introduce to you, as I said, the three different services, and I'm going to show you step by step how to use them and how to check the results that these services are producing. So we are here in the space market that Paolo just showed to you before, and if we go in the category of flood, we have here different services that are available. And I will show you three of them today. So firstly, I will start with the hazard on demand. That it's a change detection based algorithm that aims to detect the flooded areas from a pair of two Sentinel-1 images. Then I will also show you an application that allows to map flooded buildings based on also on SARS Sentinel-1 imagery. And we will also show you the automatic hazard that is
just running given on a given date, we can have generated an archive of flood images based on the Sentinel-1 imagery. So without further ado, let's start with the first application that it's called Hazard on Demand. And for this one, for this application, first we will have to create a workspace in BASDI in order to search for the images that we are going to use. As I was saying, we will use 2 images to perform a change detection operation to find the flooded area. So I will start with the simulation. So we will create a new workspace. So for this course, we have chosen an event that happened in 12th of October 2019 in Japan, in the north of Tokyo. And we will showcase you how to run the different services that I just mentioned for this specific flood event. So we can call the workspace Japan 2019, and it's Hazard on Demand. And once we have created the workspace, we will have to search. We see that you have a workspace, a classical workspace here in BASDI, and we don't have any images or data that are available in the product list. So for this, we will have to search images, and we will have to import them in BASDI so that we can run afterwards our service. So for this, we go in the search tab here. And we have different filters that we can use in order to search for the data. So of course we have the date frame. So for this, as I mentioned, the event happened in 2019 in October. So it was 12th of October. Then we can search the images, let's say 2 weeks before, to see what images were available before the flood, because we will have to choose a pair of images, as I was saying. So we will choose an image that is acquired the day of flood or the close to the day of the flood. And then we also need a reference image that was acquired before in order to perform the change detection operation. So we select the time frame. I would go from 1st of October to, let's say, 13th of October 2019. Then we have different missions of EO observation data, and here we will use Sentinel-1 images, and we have different types of images also for this sensor. Here we use, in principle, for the on-demand service, we use the ground detected images, so either the amplitude intensity images, maybe it's more familiar for the term. And then there are different sensor modes for the Sentinel-1 mission. So we have the strip map, which is acquired mainly on small islands for very specific applications, because it's a mode that covers just reduced geographical area. And then we have interferometric wide swath, which is the most used Sentinel-1 mode, and that we are also going to use for the applications that we developed in BASDI for flood mapping, because it's broadly used and it systematically acquires images with a frequency repetition of 6 days. So we can choose this mode for the mission. And then, as I said, the event was in Japan. So we will zoom here in this web GIS map, and we will select the area of interest that I said to you before, that it was in north of Tokyo. So here there are different options to select an area of interest. So now I will show you the first one, just simple. You can simply draw a rectangle for the AOI, or if not, also I will show you afterwards how you can also use the coordinate. You can manually introduce the coordinates of your region of interest. So now we can push here the search button and to see which are the images that are available and that we could import in BASDI. Okay. Oh. One mistake from my side, because you see here, but it's good also to show to you, we have different images that appeared. because there are different orbits that are available for the Sentinel-1 mission. So we have many images that were found, but I know that the orbit for this specific event for the date of 12th of October was 46. So I will introduce this parameter also in the filter list, and then we can search again, and we should have a lower number of images, as you can see here. So our images of interest are located in this area because I know that the flood happened there. So I will just reselect a smaller AOI in order to have only the below frames. So then we will have exactly 2 images in our search. Okay, so as you can see here, now we have 2 images. So there is the image of 12th of October, and the image that was acquired 6 days before. So this is the image that will be used as reference for our change detection algorithm. And then what we have to do is that we will have to import these images in the workspace that we have just created. So you have here this plus button. So you should perform this. Okay, I have many workspaces here, but the workspaces that we just created, so Japan 2019 Hazard on Demand, is selected automatically here, so we can add this product to our workspace. And here, let's see if I can move this. You should have here the status of what is currently happening. So you can see that the product is being imported to the workspace, and we will do the same operation for the second product, for the reference flood images. We also add it to the workspace. And once the images are imported, I'm going to show you how you can run the application. So the image is currently imported. It should finish quite soon. And then we can go in the, I don't know how to move this. So here we open the application from the space market, and you can see that the name is Hazard on Demand. And in order to choose the images for which we want to run the on-demand hazard algorithm, we will have to open the workspace. So it's the workspace that we just created and where we have imported the images. So in this case, it's this one, Japan 2019. And here, if we open this workspace, now we should also we have available the 2 images that we just imported in our workspace. So we'll have to select the reference image that I just mentioned to you before. So it's going to be the image acquired before the flood, and then the post-event or the flood event image. It's going to be the image that was acquired the closest to the day of the flood. Here we have the 2 different outputs that the algorithm will create. The first one, let's say, it's a little bit more advanced user algorithm, because as you probably saw in the presentation of Marco this morning, when we are applying the change detection algorithm, we are making use of bimodal mask in order to identify easily the areas that were flooded in the SAR image. So then we are also saving this mask to understand where there are the areas where the flood is occurring. So this, as I said, is for a more advanced user. And then, of course, we have the output file that is the main result of our algorithm. So it's the flood map. So here you have a name by default, and that will also use the current date of the run of the service. But if you want, you can also, for example, type the name of that you can choose for the file. So here we can put Japan 2019 10/12. And then we have different parameters that also are in line with what you saw in the presentation this morning. So as Marco was mentioning, we do a split of the image in subtiles in order to identify the bimodal regions. So here we know that the SAR images are quite large, so they cover an area of 250 kilometers square. And if we know that the flood is taking only a small % of the entire Sentinel-1 frame, then maybe it's more useful to start splitting the image already in 4 or 16 tiles for the initial run of the algorithm in order to save time. So if you want, you can either leave this parameter as a 0, so then it will start from the entire SAR image and it will start to split it. Or if you want, for example, you can fix it at 2, and then also already your image will be split in 16 tiles, and we will check if those tiles are bimodal. And then in order to check if the tiles are bimodal, we use the Ashman coefficient, which is a theoretical statistical parameter that allows to identify the bimodality of a given data set. So this is a parameter that you can fix. 2.4 is the, let's say, the classical, the usual value that we are using. Then if we want to be more restrictive to fit like very precise bimodal distributions, we can fix it up to 2.7. Or if we want to be less restrictive, where we know that we have just a few pixels of flood in our image, then we might also try to be a little bit less conservative with the distribution in order to be able to find the bimodal distribution parameters. And then we have the minimum number of pixels for the bimodal distribution. So as I said, we are splitting the image into different tiles. And for stopping the splitting of the image into tiles, when we arrive at the small, let's say, small size tiles, for example, here we can fix the number of pixels that we want to have in the smallest tile where we search for the bimodality of the image. And for example, 1,000 pixels or 2,000-3,000 pixels is a reasonable number of pixels where you can still find bimodal distribution. But again, it depends on the flood event. If you know what is the percentage of the flood that is occurring in the given Sentinel-1 scene, but 1,000 is a reasonable parameter where we can still compute some statistical parameters. And then we have the minimum blob size of the image, which is mainly related to the speckle filter that exists in the SAR images. You know, the SAR images are affected generally by speckle, and for this, of course, we can apply different filters to improve this, but we will still have some remaining artifacts. So it can be that some of the pixels that we find as flooded are just related to the speckle. So then we want to filter small groups of pixels that were detected as flooded that can be possibly due to speckles. So we can choose the minimum number of a group of pixels of an object that we can, let's say, delete from our image because they might be related to speckle, but this will not affect the extent of the flood. And we have another parameter which is not related to the algorithm itself, but the pre-processing of the data. And here I showed you that we imported the SAR images directly from the Sentinel-1 archive. So this data is not pre-processed. So we will have to put this parameter at 1 in order to pre-process the Sentinel-1 image. So that would be to calibrate, to geocode the Sentinel-1 image. But in other situations, for example, maybe Paolo already showed to you, or you can mention this, that we can also import images in PUSFATJA. And in this case, if we have some data that is already pre-processed on our PC, we can directly import it and we can run the algorithm. And then if the data was already pre-processed with Snap or some other software, then we don't have to do this pre-processing operation anymore. So we can leave this parameter at 0. So that was mostly all, let's say, to be able to run this service. And here is just the JSON file of the service where you have generated all the parameters to run the service. The workspace is open here. We have the 2 images, then the parameters are all fixed. So you just can click run. Now I will not run it in in real time because it will take a couple of minutes, let's say, and I'm not sure it will finish before the end of my talk. So I already have run some other services this week, and also for the same event, and I will show you now the results that we have. So, for example, this is a similar. It's also a service that was run for the same event. So, as you can see here, we have the two images that have been imported, the Sentinel-1 images. Then they have been pre-processed. So we have. I made two tests because I played a little bit with the parameters. But we have the two images that were pre-processed and stacked. So you can see here, this is the output result where you have two bands of the two images that are pre-processed. And then you have the outputs of our algorithm. So the first one is the HSBA mask that I told you about, and it's more a little bit for advanced users. And the product that is really of interest for you, it's going to be the flood map. So that's the last file here that was imported to WASD, that was directly generated by the service that I just showed you that we can run. And we can display it in WASD. So here you can see, here you have the navigation tab where you can see the AOI that is covered by this Sentinel-1 frame that we have used for this service. And then here you can have the result. And if you click on the band, it will be directly displayed on the map. So here you can choose different layers. For example, if you want to choose imagery, you can see exactly the areas where the flood event occurred for this specific event. And yeah, this is a way to show it. Then, of course, you can also download this result. You can click right on the product. You're able to download it, to send it to an FTP, and you can use it also locally on your PC. So that was, let's say, a brief description of this first service, the on-demand. And then if we go back to the list of applications we have for floods in WASD, we will see the second one that I want to present you. So it's the automatic urban flood areas detection. So this application, it's also based on Sentinel-1 imagery, and it allows to detect floods in urban areas. So based on the algorithm that you saw a little bit earlier today, that makes use of the INSAR coherence and also of multi-temporal Sentinel-1 information. So if we open this application, I will also show you how we can run it. So here in this case, again, we have to select the date. So here, since the algorithm, it's not based just on two images as the one that I just showed you before. So it's making use, of course, of the image that was acquired during the flood event, but also of images that were acquired before in order to compute the urban map, and also to compute the INSAR coherences to see where are the areas that are affected. We just have to give the date of the flood, and then the service will automatically search all the images from the archive that it requires in order to be able to generate this result. So here we just have to select the date of the event. So again, was October 12th, 2019. Here we can select a name of the area. So this will be a prefix for all the files that will be generated for this algorithm. And it's just just if we run different different workspaces in parallel, it's good that we have an identifier of the different files. So here we can call it again Japan in order to identify easier the area. And then we will have to select an area of interest. So this time, okay, we will not select it manually, but we can, for example, add directly the coordinates of the AOI. So there are the four corners, north, south, and west, east, that we can, for which we can add the numerical longitude, latitude coordinates, and then this will allow us to draw origin of interest. So I just noted down the coordinates for this event. I'm entering them now directly here in the interface. And then if you click on the draw option, you will have the area of interest that is directly selected. And this is the area where the results of the urban mapping algorithm will be generated. And then in the advanced tab, we have again some different parameters that are related to the algorithm itself, but again also to the search of the images and this characteristic that we need in order to be able to generate this result. So I'm not going to go now in all the details. These are because, as I said to you, this algorithm it's quite complex and it requires different types of data from the past. So it requires, for example, ground detected images in order to be able to detect the bright area in SAR images. So that would be the buildings, but it can also be other classes. So in that case, we are also using the SLC images to generate the in-SAR coherence that will allow us to filter and have a precise building map. And then also there are some SLC images that we are using in order to generate the in-SAR coherence that is related to the event itself. And then we will also have an in-SAR coherence that was acquired before the event. And we will compare these two in-SAR coherence maps in order to identify the areas that are flooded. And then we intersect these regions with the urban map that we also have extracted from the Sentinel-1 image. Here we have the data provider. There are different data providers. Maybe Paolo can say something about this to you if we have time. And again, the orbit filter, which is quite important, especially for this application, because, as I said, it requires a large number of images, so it will take a little bit of time to produce the result. So then it's always good to fix the orbit if we want to have the result as soon as possible. Okay. So that would be all, I think, as parameters for this application. Then we have here advanced, but these are mostly, let's say, implementational details that I'm not going to enter now. And here, of course, what is important, if you have already created a workspace in which you want to run this application, you can open it from the list of available workspaces that you have. Here, for example, I created an ADB building a flood map. We could open this one. Or if not, you can also select this option to create a new workspace, and WASD will directly create a new workspace that will be available for you, and where the results of the urban mapping algorithm will be available. So then you can just run this application, and now I will show you the result of this application. So as I said to you, there are different images that were used in order to produce the urban map. So here first I will show. Let's select them. See the same procedure as I showed you before. We can use different base maps to check our results. And the first one of the important results that this algorithm is producing is the urban map. So this will show us. You see that is for the AOI that we selected. We have the urban map that was generated. So these are the building. This is the building footprint. And then after we get the in-SAR coherences, these are all the files we have here available here. So we have the pre and post in-SAR coherences that we use to detect the areas that are flooded in the urban footprint, and we use those layers, and then we intersect them with the urban map. And here we can see on top of it another layer that we have generated that showcases the floods that occurred in urban areas. So yes, these are the two main results of this algorithm. Again, you can download them, you can display them here in WASD. There are different options in order to check and play with the results. So that was for this second service that allows to to delineate flood in urban areas. And then if we go again to the list of services that we have available in BASDI for the flood category, there is also automatic hazard that we can use, which is a service that allows to generate an archive of flood maps based on Sentinel-1 images was developed, as Patrick was saying before, in the framework of the eDrift project. So if we open this application, you will see it's something very simple to use, because here you don't have to search the images, you don't have to fix too many parameters. Again, we will select the AOI. So I will introduce the same AOI as we did before. We draw it. Then we have the AOI of interest. We select the date of the event. Again, 12th of October. And then we can also, as I said to you, we can choose a prefix of the file names that will be generated for this service. Again, here you can open the workspace of interest. I should have one ADB flood archive, for example. Okay, and sorry. And then in the advanced parameters here, there are some parameters that are interesting, I would say, for you, that are related to the search of the images. So as I said, this service allows to generate an archive of flood events. And we can choose the number of images that we would like to search that were acquired before the flood event. If we know that it's let's say we are interested in the status of event happening this week, but we know that there was already a flood ongoing, which I think it's the case for different, can be the case for different regions in Indonesia. We know that the flood was already ongoing, so we know that the flood started 2 weeks or more before. We are able to select a number of images for which we want to go in the past to generate flood maps. So for example, here, if we select 15, it will search images with respect to the flood date that we are giving 15 days in the past, but we can even select more, like 24 images like this. We know that we will have, for example, more or less 4 Sentinel-1 images from the past that will be used for a given orbit, because the repetition frequency of the Sentinel-1 imagery acquisition is 6 days in general. And then also we have the number of days that we would like to search after the flood event. So if we know that the flood is still ongoing, or if we want to see if the flood has completely reduced, so there will be no more changes, we can also select this parameter. So you can play. There are different configurations that you can choose here. Then of course there is the data provider, and here again there are the same parameters of the change detection algorithm itself, because here it's generating the flood archive, but the main principle of the HSBA on demand is also used here, because we are going to detect the flood in the SAR imagery by using pairs of successive 2 Sentinel-1 images. So again, here you can put the HSBA depth. You can start from 0, from 1, depending on the number of tiles you would like to already have split the SAR image. Then the Ashman coefficient that I told you before, it's used to detect the bimodality of the Sentinel of the image. Then the number of pixels and so on. I don't think now I will go again in these details. So these are the main parameters of this service. You can simply run it, and then I will show you here. I should have the result, yes, of the flood event from Japan again. But here, as you can see, when I told you this was let's say flood event that lasted for a couple of days and didn't affect a very large surface. So, for example, if we have here, I generated the flood event starting with 24 days before the flood had started. And for example, here we have the flood event for the date of 11 of October, so it was just before the flood happening. So you can see here that there is no flood at all for this date. But if we click the date of 12th of October, we can see that we already have the flood that is ongoing. And then if we go further on, for example, for the 13th, there should be some regions where the flood is increasing. So you can see here there are some areas where we have some flood that is still remaining from the 12th of October, still on the 13th. So if we deselect now this, and then, for example, we go on the 17th of October, there should be again no more flood, because as I told you, the flood happened just for a couple of days. So that was something to show you for the result of this third service. And I don't know if we still have time. I also have a result from Jakarta from the on-demand service that I can show to you, but it's not mandatory. Patrick, can you hear me?
Yes, I can.
We are still okay with the time. Can I still show an example, or?
Yes, I think we have still a bit of time. Because when you were not there, Paolo already presented pre-calculated data sets that are available. Mm-hmm. So we will need still after you about 15 minutes for Paolo to explain how users can deploy their workflows on WASDI. But if you have maybe for 5 minutes, would that be okay?
Yes, I can re-show again how to use the on-demand service for a specific event that occurred in Jakarta in 2020.
Okay, thank you.
Okay. So then here, again, for this event, for example, that happened in Indonesia in 2020, at the beginning of 2020, I think we were probably aware of this event was a quite huge flood event. So here, for the same procedure, we should import firstly the images in the WASDI workspace. So we select a region of this on the city of Jakarta, and the event happened in January 2020. It was the second date of the flood. And then we should go a little bit, say 2 weeks before. The image filters are the same, the ground detected images we are using, and the interferometric white spot mode, and I think the orbit was 98. And then we can also search for these images to see if they are available. Yes, here we have, for example, we have 2 frames that were acquired, and they are, let's say, covering, the 2 frames are covering the area of interest. So then what we can do here, for this case, I will show you the results. I already have the results for the upper frame, but it would be interesting also to generate the results for the lower frame. So then, for this case, we just reselect a smaller AOI in order to select the 2 frames that were acquired in this southern region of Jakarta. And then, for example, we can add these two frames to our workspace. So let's say I will add them directly to the Jakarta flood event. I will change now that. workspace. I will import the 2 frames in the workspace of interest. And now if I go to this workspace, you should see that the images are currently being imported in our workspace of interest. It's just to show you that we can run, for example, in parallel the same service for different pairs of images. Because here I have the results that I already generated. I had already imported 2 Sentinel-1 images for the frame that was acquired in the north of the city of Jakarta, and here are the pre-processed images and the 2 results that our algorithm is generating. And here there is the flood map result for this upper frame that you can see here. But it's not covering, as I was saying, the region below. So for that reason, we are now currently importing the images in the southern part. So they are currently being imported. Okay, the import has finished, and for this we have to go again in the App Store, and we can choose the Hazard on Demand service. Okay, we open the application and we go again in the workspace of interest. So for us, the workspace of interest in this case was the Jakarta flood event. So here you will see that we have different images that are currently available in the workspace. So we have already the images that we imported for the north part of Jakarta. And then we have the results that were generated by our service. And then we also imported, for example, the frames that cover the southern part of Jakarta, and we can choose them to run and again the service for a new pair of images. So here it's the image that was acquired in December, so before the event, December 2019, and then the image acquired for the southern part on the date of the flood events on the 2nd of January 2020. Okay, here, as I told you, we can change again the file name. We can put Jakarta 2020, and we can put South. And then the parameters. The most important here is not to forget to pre-process the images, because these are the raw images that were imported from the Sentinel-1 archive, and these ones we can leave it, let's say, as it is, and we can just run this service, and afterwards we should be able to have in, let's say, plus minus 15 minutes the results for this other frame that is covering the flood event that happened in Indonesia in 2020. So with this, I think I can close my demo. I don't know if you have now some specific questions, maybe you can ask them directly, or if not, for sure you can write us emails, or we will provide you some slides that showcase these steps that I just showed you today.
Thanks a lot, Ramona. That's also what I wanted to say. So all the what you showed now is also available as in form of a tutorial on the shared folder. So you can repeat the same processing steps that Ramona just showed to get familiar with the platform and the different applications that are currently available. Paolo, would you have still time to make a quick demo of WASDI beyond Hazard? So what other EO applications can be deployed on the platform by expert users?
Sure, Patrick. Okay, sure. I will take very few minutes. If I'm not wrong, we should have the break in 8 minutes, something like that. And I think that all the participants are very kind and maybe also tired after all this stuff. So I will try to be as quick as possible. And sorry, I'm making, okay. Just really 5 minutes to give you an idea of what is possible from the expert point of view. We have mainly 2 features that are that can be of interest of the expert. One is for really let's call it you expert again, not developers. Okay, I suppose that you all know Snap, the software Snap. Okay, it is the ESA open source software where you can create your own workflows. Okay, here I already have created one that takes Sentinel-1 GLD images and make apply a bit file, remove border, and so on. But this is just an example. You can make the workflow as you want. And in WASI there is this feature, you can go and save it. So I can save it in my computer. Okay. I call this S1 GLD. Okay, perfect, save. Now that the XML is saved, well, I will need to ingest to find a Sentinel-1 GLD image that can be used. Sorry. Okay, search. So I take one image just to run the sample. When you are in the editor, okay, you have all the different workflows here. Again, as it was for the workspaces, also the workflows can be shared with other users, can be made public or private, and you decide. So I just click here on the new workflow, and I open a folder of my computer. Okay, if it was in ctemp and delete modify. Okay, this is the file that we saved 1 minute ago. You just drag and drop it in WASD. Okay, give a name. S1 GRD live test. Okay, you can put a description. You can decide if it is public or not. Okay, and just click apply. At this point, we should have our new workflow uploaded in WASD. In the meanwhile, maybe you have seen the green display. Our Sentinel-1 images arrived, but here don't have yet. Okay, let me refresh this window. Okay, S1 GRD live test. Okay, our Sentinel-1 image is started, and you just click run. Now, if everything goes smooth, always we are live, but your workflow will be executed immediately online. Okay, was okay live demo. Sorry, it is I don't know what happened, but we will check obviously. But this usually works very well, and let me see if I can quickly make another one, maybe for Sentinel-2 images in this moment. Anyway, the concept of this functionality is that you can imagine that if you are used to pre-process many images, okay, you can use this possibility, because obviously, again, this is scale in the cloud, so you can decide how many images you want to process. Okay, the same concept is instead available for the programming language. Okay, let me just take a look if we can make a different vegetation index for Sentinel-2, just to have one index that can work quickly. Connect graph, save, ramp, my graph, say, let's go here, again, in the workflow, new processing, again, test live. This is a different workflow. Let me see if we have it now. Test live with a certain 2 images run. And I hope, no, I don't know. I was saying that in the meanwhile, the same concept is extended for the code. So was this designed to let you work, okay, with different programming language. You can see that now the second instead was correct, it is running correct. In the documentation, you will see that we support different programming languages. So we support Python, Octave, MATLAB, Java, and also IDL, that is still not listed here, but will be added very soon. What we propose, okay, is here is a tutorial in Python, okay, just a sample. The concept is what we say, develop at home and deploy to the cloud. No? So if you have your own algorithm, your own processor, maybe for flood detection, maybe you have it. I'm pretty sure that I know that Lapan, for example, is very strong, and many entities in Indonesia have a huge experience in this kind of applications. So maybe you will have your own processor, okay? The concept is that in WASD, you can easily work your environment as you are used to. And when you want to add a new application, you just have to import the WASD library that are available in all the languages. Then when you finish your code, just zip your source code, a zip, drag and drop here, and you add a new application. From here, you see the different kind of application supported, okay? And this is, in our opinion, one of the most strong points in WASD, because you can deploy to the cloud immediately without any need of IT support. And you can check your log online. You can, once the application is deployed, you can update it. And this, again, allow you to run your code, but not to your computer, but on a cloud environment that can scale up, access all the images of the catalog, and all the computing resources. Remember, obviously, that you will decide who will see your application. You can decide to make it public or private. You can decide to share with some specific users, okay? And if you can decide to show this in the App Store or not. So the application developer has the full control of this aspect. I mean, time is gone. I think that we said a lot of things. So from my side, obviously, thank you very much to all. We are available for any question. Let me just remember that to you that we have, in the context of this project, we have officially until the end of January, but we can say for sure 3 months of free test access. So just write an email to us, and we will send you back the link for registration, okay? And you will have 3 full months to test, access the spaces, run application, if you want develop whatever. Then there are plenty of solutions. Really, we are really flexible in time for the future. We are much more interested that you before you test it and see if it's something that can help in your work. That's all from my side. I leave the floor. Don't know, Patrick, Nancy.
Thanks a lot, Paolo. Yeah, I would like maybe just to add to what you just said, Paolo, that for those that are not interested in now running their own processes, we have to find out what's the best way to share maybe pre-calculated maps. So the archive of floods from 2015 to 2020, the water bodies map. I mean, this information might be also useful for people who are not now eager to start processing data on WASD. So maybe this is something we have to think about how we can share the data more easily.
Well, sure. For the other workspaces, if they have an account, we share the workspace and they can just download it. The flood archive maybe is bigger, but give us a request and we can give the files in the way you prefer. No problem at all. That's from my point of view. I hope this answer.
Yes. Thanks, Paolo. So maybe I give the floor now back to Nancy. I think we are supposed to have a break, and then we will continue with another session where our colleagues from Indonesia will tell us about their activities.
Okay, thank you for all the lectures, for this very such interesting presentation. Unfortunately, we have a time limit. And once again, we would like to say thank you to Patrick Megan, Marco Cini, Paulo Campanella, and Ramona for the very interesting session and how the remote sensing and WASD platform can be used to support the disaster resilience, especially flood in Indonesia. Once again, we would like to say thank you and terima kasih. Bapak dan Ibu, seperti yang disampaikan tadi oleh tim pengajar, jika Bapak dan Ibu ingin mencoba platform WASD, Bapak dan Ibu dapat mengirimkan email melalui info@wasd.cloud. Baik, untuk melanjutkan sesi berikutnya, kita akan rehat sejenak selama 5 menit, dan kita akan kembali bergabung pada pukul 16.27 untuk mengikuti sesi berikutnya. Terima kasih. Bapak, Ibu, dan rekan-rekan sekalian, semoga masih tetap semangat ya mengikuti acara hari ini. Kami masih melihat ada sekitar 80 peserta lebih yang masih tergabung dengan Zoom meeting ini. Tadi kita telah mendapatkan ilmu-ilmu yang menarik dari para pengajar, dari LIST dan dari WASDI. Kini saatnya kita mendengarkan sharing session, yaitu dari pakar-pakar di Indonesia, dari Institut Teknologi 10 November, serta peneliti dari Lapan BRIN. Dan dalam sesi ini kita juga akan bisa berdiskusi bersama-sama. Acara ini akan dipandu oleh Dr. Firman Hadi. Kepada Dr. Firman Hadi, kami persilahkan Pak Firman. Kalau 2 hari kemarin kita narasumbernya bapak-bapak, hari ini mungkin Pak Firman juga lebih semangat karena ada Ibu dari ITS dan dari Lapan BRIN. Waktu dan screen kami persilahkan ke Pak Firman.
Iya. Terima kasih Bu Nancy. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore. Karena tadi Bu Nancy menyinggung berasumsi ya, saya bersemangat sebenarnya tidak ya. Tapi saya bersemangat sekali. Karena yang memaparkan ini bukan saya, bukan dari sisi gendernya ya. Tapi lebih dari umur. Melihat CV-nya ini masih muda-muda sekali nih, namun banyak riset ya, terutama terkait dengan banjir. Nah, jadi topik pada hari ini berkaitan dengan pada sesi ini ya, pada sesi sore ini berkaitan dengan banjir dari para peneliti muda. Ibu Dr. Filsi Bioresita ini dari ITS, kemudian dari Institut Teknologi Surabaya ya. Kemudian Ibu Hanalisti, peneliti dari Lapan BRIN. Nah, yang menarik, kita akan sama-sama menyimak pendekatan dari sudut pandang yang berbeda ya. Kalau peneliti biasanya waktu proses yang lama atau apalagi ya, mencari metode yang terbaik itu menjadi salah satu fokus ya, atau keterbaruan dan sebagainya. Tapi ketika kita berhadapan dengan pengambilan keputusan, misalnya ini kalau terjadi banjir, apa yang harus kita analisis? Nah, itu kan butuh kita berpacu dengan waktu. Nah, jadi di sini ada 2 hal yang mudah-mudahan dapat kita cari ya, dapat kita dapatkan ya, benang merahnya seperti apa sih? Apakah ada temuan-temuan baru dari riset-riset di universitas atau dari peneliti, walaupun Ibu Analisi juga peneliti ya, tapi kalau dari topik yang akan disampaikan itu kan lebih kepada bagaimana menyediakan hasil dalam konteks respons bencana ya. Dalam ini ada internasionalisasi charter. Ini kan berpacu dengan waktu ya. Saya masih ingat dulu waktu ketika masih di GIC, pengalaman yang tidak dilupakan ya adalah terkait dengan bencana gempa di Nepal. Jadi mungkin Pak Syam juga masih ingat, data begitu banyak, 2 minggu kita nggak ngapa-ngapain. Saya dimarahi ya saat itu oleh Dr. Lal dalam tanda kutip. Jadi itu pengalaman berharga di mana ketika terjadi bencana kita berpacu dengan waktu. Nah, tanpa berpanjang lebar lagi ya, Ibu Filsa ya, Ibu Filsa Bioresita dan Ibu Hana, ini kami berikan kesempatan masing-masing 20 menit. Ya. Ketika akan berakhir mungkin nanti saya akan chat pribadi, tapi biasanya ketika presentasi lupa ya, harus membaca chat. Jadi mohon maaf apabila nanti ketika memang sudah 20 menit saya akan memotong supaya nanti kita ada waktu untuk diskusi. Terima kasih. Saya langsung saja kepada Ibu Dr. Filsa Bioresita untuk memaparkan. Memang yang pertama Ibu Filsa ya, benar ya?
Iya betul Pak.
Ya.
Terima kasih. Suara saya terdengar jelas ya Pak ya?
Iya.
Terima kasih. Saya izin share screen ya Pak. Mohon maaf Pak Firman, apakah slide saya sudah terlihat?
Sudah terlihat, ya.
Baik, saya langsung mulai ya. Ini saya pakai bahasa Inggris tidak apa ya Pak Firman, supaya semuanya bisa ini.
Saya jangan bahasa Perancis, Bu.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. So my name is Filsa Birosita. I come from the Department of Geomatics Engineering Institute Teknologi 10 November, Surabaya, Indonesia. It's an honor for me to be part of this event about the knowledge sharing and capacity building of Earth observation services for water and food security planning in Indonesia. So today I would like to present you about the Earth observation for floods monitoring, so using also the Earth observation data. But first, why floods? Why floods monitoring? Why we have to map or monitor the floods inundation spatial distribution? So we know that from this graphic, about 25.3% of global damage caused by natural hazards are due to flooding. So floods can be considered as the most costly type of hazard in terms of property damage and fatalities. And also based on BNPB data in the 2020, we know in here that floods is the most frequent disaster occurred in Indonesia in 2020. In here, you can see the data in here. And also, but based on the monthly data in 2020, floods again became the most frequent disaster occurred in Indonesia. As you see in here, there's some pictures which visualize the floods in the South Kalimantan, in Aceh, in Batu Es Java, in West Sulawesi, in East Nusa Tenggara, and also in Maluku. It's spread across in Indonesia. So it means that floods occurred not only in one area in Indonesia, but in many areas in Indonesia. So for flood inundation mapping as part of flood disaster mitigation, before we use the field surveying, but right now there's the remote sensing data. Why we use remote sensing? Because it's can use for frequent and large scale research. So we can use the frequent large remote sensing data to be able to monitor the floods inundation. And then it's also dynamic. The remote sensing data is dynamic, it's real time, and also it's low cost compared with the field surveying. We know that there is two types of remote sensing data. There is active remote sensing and also passive remote sensing. And there are many satellites related with the active and passive remote sensing data. We know as for the passive remote sensing data, there's optical data like MODIS, Landsat, Spot, Iconos, etc. And also for the SAR data came from the active remote sensing data. There is data like Envisat ASAR, ALOS PALSAR, RadarSat, TerraSAR X, and many more. And right now, with the Earth observation data, such as Sentinel-2, come from the optical data, and also the Sentinel-1 from SAR data. Since 2014 and 2015, we can get the massive data from this two type of satellite data. They provide high spatial resolution and also high temporal resolution, up to 6K in here. So we know in here that with the Sentinel-2, we get about 10 until 12 meters, 20 meters. And then also for the Sentinel-1, we can get about 20 meters. So what is the challenge with this massive data? So the challenge with this massive data is that high temporal frequency leads to high volume of data, which implies to propose new methods for data processing and analysis, as conventional methods will not be sufficient to account for this temporal dimension and to manage massive data. So manual processing methods are not compatible with time series data and multi-source data. The manual processing method use expert intervention, which must be reduced through automation in the processing chain to obtain information quickly and efficiently. To solve this challenge, we try like an automatic method, or right now it's really popular using the cloud computing such as Google Earth Engine. We know before from the training, we know that there are also another services provide cloud computing. So this is the existing product, tools and service. I list only some of them, so it's not all. I know that before there's another services and tools for surface waters and floats mapping. For existing products or for databases at global scale, there's a SRTM water body. There's also global lakes and wetland database. There's a water and wetness, and also there's a global surface water. For tools and services, there's a surface water mapping tools, Water Skill Viewer, WAMA Pro, Terasar X Float Service, Tandem X Water Indication Max Processor, and then there's also FNFCE, Water Detection Tools. And what I used before is that there is a service come from Copernicus. It's called Copernicus Emergency Management Service Mapping. It's for map floods in Europe and also in some area outside Europe. It's really interesting, this one, this Copernicus. Okay. As for methods, yeah, because Pak Firman before told us about the methods, yeah. As for the researcher, we really interesting with the methods to be able to mapping the floods inundation, to be able to get the optimal results. We know in here for mapping flood inundation or for surface water also there is methods called thresholding. And we can use it with the manual thresholding or automatic thresholding. As for manual determination can be done by visual interpretation of image histogram and trial and error procedures. So as we can see in here in the picture, so if we have like a histogram of the image, which consists of water and non-water, then we can get the threshold to be able to separate between water and non-water. There are also automatic thresholding with the methods such as Otsu algorithm, Valley emphasis, and statistical modeling of histogram. Another method is unsupervised and supervised classification. This method is really useful, and many people already use this one to map surface water for land cover and also for floods mapping. And there are also methods called OBIA. Okay. This method is for very high resolution satellite imagery data because the Earth surface in the very high resolution satellite imagery data are usually larger than the pixel size. Therefore, although pixels represent different spectral properties, they can be the same object. So right now, OBIA has grown increasingly in surface water mapping over the last few years to address this issue. This approach has the advantage of improving classification with a combination of spectral data and also contextual information. This one, I tried to propose some methods, these automatic methods, but it's not in the cloud computing process. We have to do it using Snap or using the programming like R program or MATLAB. So this one, using the Sentinel-1, which is also part of Earth observation data, we can use the during event and post event of floods, and then doing some processing image stealing, this step by step to be able to extract the spatial distribution of floods inundation. So first, we know that for pre-processing, we do some apply orbit file calibration to be able to change the data to sigma node or another like a gamma node, beta node. You can choose in there. But in the methods that I propose, I'm using the sigma node data, and after that doing some speckle filtering to be able to reduce the speckle noise, and then after that doing terrain correction as for a geometric correction. After that, rather than using like a global thresholding, in here I'm using like a modified split-based approach, which means try to divide the Sentinel-1 image into tiles, and then we can select the tile which have water and non-water inside. So we will not use the tiles which didn't have water inside in order to process with this method. So we can choose it with the Hartikan deep statistic value, and then get the tile selected, and then we use the tile selected for finite mixture models. So creating models in order to separate between the water and non-water area, and then get mean sigma lambda. So in here, we not directly fix the thresholding value, but in here we try to get the mean sigma lambda from the 2B model histogram in here. I'm sorry, from B model histogram in here. Okay. After that, we do the smooth labeling using bilateral filtering. So after the class modeling, we can get the binary image consists of water and non-water, but there is some noise in here. Okay, so we do some smooth labeling in order to get the fixed surface water and non-surface water. And then to be able to extract the surface water, we can do some thresholding in here. We say that the pixel value more than 0.9 become the surface water. And then we do some subtraction between during event and post event to be able to get the temporary surface water map or a floods inundation map. And we evaluate or assess the accuracy of the result using some like this one, a classic accuracy result using the methods like overall accuracy, F measure, etc. in here. This is the result, one of the results using these methods. First is floods in Sentani, Papua in 2019. In here, we can get in here the floods inundation area is next to the Sentani Lake in here, and also in the second area in here above the Sentani Lake. And also this is another result using the methods in Ireland for floods in Ireland in 2015 and 2016. And this one is in the zone French in 2018 in here. So the blue one is the floods area, floods inundation spatial distribution visualized by the blue color in here. And right now it's really popular using Google Earth Engine with the code from United Nations, which can be accessed in this link. And also there's a code like the tutorial and the code in this link. So the methods is for change detection and thresholding. So they use in the code using GAA using the change detection and threshold. So it's almost the same with the method before, but the difference is that in here they use a global threshold. So they use the change detection first, and then after that apply the threshold. So it's a little bit different from before, because before we did the thresholding first, and then after that did change detection using subtract. But this one, the change detection is applied by divided the before flood mosaic, divided the after flood mosaic by the before flood mosaic, and then the height values or bright pixel indicate the height change, and then low values, depth pixel, indicate the little change. And then after that, we can get the binary image based on the threshold defined in here. This is the result, like one of the result using this Google Earth Engine, floods in South Kalimantan on 20 January 2020. In here, we can see the blue one is the permanent surface water, like a river, and then after that the red one visualize the spatial distribution of floods inundation. That's all from me. Thank you so much. Be back to Pak Firman. Terima kasih.
Terima kasih Ibu Filsa atas paparannya ya, menarik bagaimana memanfaatkan Google Earth Engine ya. Dan kemudian metode yang diterapkan biasanya kan dibuat hard coded ya. Threshold-nya itu misalnya minus 3 dB. Nah, di sini dibuat dinamis dengan menggunakan output threshold ya. Jadi cukup menarik. Walaupun nanti mungkin ada yang bertanya ya, ada pertanyaan yang lebih lanjut. Saya juga sebenarnya ada pertanyaan, tapi saya simpan dulu supaya lebih banyak lagi nanti pertanyaan. Jadi untuk kesempatan berikutnya kami persilakan kepada Ibu Hana untuk memaparkan makalahnya begitu atau tulisannya, ilmunya. Kami persilakan.
Ya,
silakan.
terima kasih Pak Firman.
Ya.
Share screen. Sudah terlihat Pak?
Iya, tapi suaranya sepertinya agak jauh ya, walaupun memang jauh sih, Bandung dengan Jakarta jauh ya.
Saya Jakarta Pak.
Iya, maksudnya.
Bapak di Bandung ya Pak?
Iya.
Siap Pak, mangga Pak.
Mungkin kurang dekat dengan mic-nya.
Oh ya, baik. Sekarang sudah jelas Pak?
Ya, cukup.
Cukup. Oke, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Izin saya menggunakan bahasa Pak. Hari ini saya akan menyampaikan sharing dari kegiatan yang ada di LAPAN. Seperti kita ketahui kalau LAPAN itu pasti identik penelitian dan pengembangan kedirgantaraan maupun pemanfaatan keantariksaan. Di sini saya akan menyampaikan bagaimana aktivitas lainnya di LAPAN terkait quick response terhadap bencana banjir yang ada di Indonesia. Perkenalkan, saya Hana Listi Fitriana, saya peneliti dari LAPAN. Tadi sudah disampaikan oleh Pak Firman juga. Untuk yang melatar belakangi salah satu kegiatan kami, sebetulnya sudah disampaikan oleh Bu Filsa tadi juga. Kenapa? Karena banjir ini merupakan bencana hidrometeorologi yang sering terjadi di Indonesia. Menurut perhitungan kami itu sekitar 32% lebih besar frekuensinya dibandingkan bencana lain yang ada di Indonesia. Jika dilihat dari grafik ini, jika tadi Bu Filsa sampai 2020, saya menambahkan sampai 2021 di bulan Juli, di mana distribusi banjir ini tersebar di seluruh wilayah Indonesia dari Aceh sampai Papua, yang telah menyebabkan 9.112 kejadian banjir, di mana selama 10 tahun belakang ini telah menyebabkan 2.184 korban jiwa. Peristiwa besar banjir ini dan dampak-dampak yang ditimbulkan dari banjir ini memerlukan perhatian yang khusus. Sehingga LAPAN di sini berperan untuk memberikan informasi berbasis remote sensing, salah satunya untuk bagaimana stakeholder ini dapat mengambil kebijakan dalam manajemen bencana. Selain itu juga, LAPAN tergabung dalam Internasional Charter Disaster, seperti yang disampaikan oleh Pak Firman tadi, di mana semua community dalam lingkup Space Agency ini bersama-sama memberikan informasi dan produk untuk mendukung respon terhadap bencana. Dan LAPAN juga sebagai Regional Support Officer, di mana kami mendukung atau memberikan informasi berbasis data remote sensing di Indonesia atau di berbagai negara. Ini salah satu contoh International Charter yang telah kami aktifkan, yaitu kemarin untuk Cyclone Seroja yang telah menyebabkan banjir bandang dan longsor yang ada di NTT. Kami bersama-sama dengan komunitas, termasuk dengan AIT, dibantu dalam memberikan informasi. Karena seperti yang Pak Firman tadi sampaikan juga, kalau International Charter banyak sekali data-data yang masuk dari berbagai negara. Jadi kami berkolaborasi baik dengan universitas maupun stakeholder lainnya dalam memberikan informasi terkait dengan bencana yang terjadi. Biasanya data yang kami gunakan untuk memberikan informasi banjir ini adalah data-data yang kami akuisisi sendiri, yaitu mulai data optik sampai data SAR, dari yang low resolution sampai yang very high resolution. Untuk data Himawari sendiri, kami menggunakannya untuk data meteo, kemudian data Landsat, Sentinel, Untuk high resolution-nya sampai very high, kami menggunakan data SWOT, World View, dan Pleiades. Seperti kita ketahui juga, jika curah hujan merupakan salah satu trigger untuk terjadinya banjir di Indonesia. Dengan ini kami membuat suatu portal khusus, yaitu di mana diakses di modis katalog.lapan.go.id dengan menggunakan data Himawari 8. Dengan menggunakan data Himawari 8 ini, di mana resolusi temporalnya per 10 menit, kita dapat melihat bagaimana sebaran dan intensitas dari terjadinya curah hujan yang ada di berbagai wilayah di Indonesia. Ini merupakan salah satu data yang biasanya kami gunakan, yaitu data Sentinel-1. Mungkin secara detailnya tadi sudah disampaikan oleh Dr. Marco, oleh Dr. Filsa juga. Dari sini kita dapat melihat perbedaan bagaimana data Sentinel-1 ini dapat memberikan informasi sebelum dan sesudah banjir. Pada yang saya lingkari merah ini bisa terlihat bahwa perbedaan sebelum dan sesudah cukup kentara, di mana yang sesudah pada tanggal 11 Juni ini terlihat berwarna biru, itu merupakan kejadian banjir. Begitu pula untuk data di awal tahun 2021 ini, di bulan Februari untuk di Pekalongan, bisa terlihat warna yang lebih terang di yang sebelum, dan warna yang lebih gelap di setelah banjir. Untuk metode sendiri, karena seperti yang disampaikan Pak Firman tadi, quick response ini berpacu dengan waktu. Kami harus memberikan analisis yang komprehensif, tepat, tapi juga cepat. Maka kami di sini menggunakan metode change detection. Tadi detailnya sudah disampaikan juga oleh Dr. Marco dan Dr. Filsa juga. Kami menggunakan dua data, yaitu sebelum dan sesudah. Kemudian kami men-thresholdkan untuk mengkelaskan mana yang banjir dan tidak banjir. Ini merupakan informasi yang kami sampaikan ke stakeholder yang ada, yaitu pada 10 Juni 2019, yaitu di Kabupaten Konawe, di mana dengan menggunakan data Sentinel-1 dapat terlihat bagaimana deteksi banjir dapat dilihat dari data citra Sentinel-1. Yang cukup hangat di awal tahun 2021 yaitu banjir di Kalimantan Selatan. Kami memberikan informasi menggunakan data Sentinel-1 juga, di mana data Sentinel-1 telah berhasil dan cukup baik untuk memberikan informasi deteksi banjir yang ada di Kalimantan Selatan. Ini contoh di Provinsi Jakarta. Oke, selain informasi-informasi awal tadi, yaitu bukan hanya deteksi banjir, kami juga melakukan informasi lanjutan sesuai dengan kebutuhan atau dampak yang dirasakan. Seperti pada di kejadian di Pantura, yaitu di Kabupaten Karawang, Subang, Indramayu, dan Cirebon, kami melakukan pengolahan lanjutan, yaitu kami harus memberikan informasi berapa luasan banjir yang ada di sawah dan bukan sawah. Kenapa? Karena daerah Pantura ini atau di Karawang ataupun Subang, Indramayu ini merupakan banyaknya persawahan, lumbung padi yang ada di Indonesia salah satunya. Sehingga informasi ini cukup diperlukan untuk melihat berapa banyak gagal panen yang akan terjadi di wilayah tersebut, dan berapa banyak juga subsidi yang harus disampaikan oleh pemerintah ke para petani. Begitu pula untuk Kabupaten Pekalongan. Selain informasi tadi, kami juga memberikan informasi lanjutan menggunakan data high resolution, karena dampak yang ditimbulkan oleh banjir ini cukup besar, sehingga kami memberikan informasi berapa banyak area yang terdampak, berapa banyak bangunan yang rusak. Dengan menggunakan data Pleiades ini dan data Sentinel-2, kami dapat memetakan berapa jumlah bangunan yang terdampak oleh kejadian banjir. Mungkin di sini lebih terlihat dengan jelas bagaimana sebelum dan sesudah kejadian banjir di desa Nelelamadike ini. Pada garis yang merah itu terlihat di sebelah kiri bagaimana
sebelum kejadian banjir, bangunan masih tetap kokoh dan cukup padat. Akan tetapi pada saat terjadinya kejadian banjir, banyak sekali bangunan yang luluh lantah dan hampir terlihat bangunannya rata. Untuk informasi quick response ini sendiri dapat diakses oleh publik di si Pandora 8 maupun di aplikasi si Pandora di Android. Selain informasi dari quick response ini, di si Pandora juga terdapat informasi lainnya seperti sumber daya alam, lingkungan, peringatan dini, dan tanggap darurat lainnya. Demikian sharing yang saya sampaikan. Terima kasih banyak. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Dari sesi ini sepertinya saya mendapatkan kesan ya, bahwa kaum ibu-ibu itu tidak banyak bicara ya. Kalau sesi sebelumnya, saya kesulitan sekali untuk memberitahu kepada narasumber ya, untuk menyetop presentasinya begitu. Kalau di sini lebih cepat ya, jadi kita punya banyak waktu untuk ngobrol ya. Nah, sepertinya kalau ngobrol ini akan banyak ini yang keluar nih. Kalau presentasi secukupnya saja, efektif dan efisien yang disampaikan oleh Ibu Hana ya, juga Ibu Filsa. Kalau dari Ibu Hana ini lebih ke bagaimana analisis dilakukan untuk membuat produk yang dapat digunakan selanjutnya, dan tidak hanya produk ya, tapi value added product, di mana ada nilai tambahan, bukan hanya flood extent, tapi juga ada informasi wilayah desa apa saja yang terkena, ada berapa bangunan yang terdampak dan sebagainya. Nah, mudah-mudahan ya dari audiens ini banyak pertanyaan. Kalau dari saya sudah mencatat sih pertanyaan dari saya pribadi, tapi kan tidak adil dong kalau saya yang bertanya duluan begitu. Ya, kami berikan kesempatan kepada Bapak Ibu untuk berdiskusi dengan kedua narasumber ini. Bisa lewat chat ya, atau bisa langsung mungkin mengangkat tangannya ya. Jangan angkat kaki ya, kalau angkat kaki nanti leave meeting. Belum ada? Mungkin dari Kang Sam sini sebagai mitranya Ibu Hana. Ada pertanyaan?
Ada pertanyaan itu di chatting kan? Coba cek.
Oh, di chatting ada.
Ya.
Oke. Ada pertanyaan dari Marco ya. Oh, bukan ini. Ini informasi ya. Chat. Ini sudah langsung ya, sudah langsung dijawab oleh Ibu Filsa. Nah, lagi.
Yang terakhir Pak Firman ada untuk ke Bu Hana, untuk ke data curah hujan kalau nggak salah.
Oh ya, ya ini saya sudah saatnya memakai kacamata nih. Tidak terlihat ininya apa tanda tanyanya. Ya, ini ada pertanyaan. Sumber data curah hujan yang digunakan. Apakah datanya dapat diakses gitu?
Ya, terima kasih Pak Firman. Terima kasih Paulo untuk pertanyaannya. Untuk data curah hujan bisa diakses baik itu melalui portal Lapan maupun GME langsung, karena ini merupakan data Himawari 8 yang berasal dari data satelitnya milik Jaksa.
Jadi data yang sudah siap pakai ya, jadi tidak perlu diedit lagi.
Ya, betul.
Karena format datanya kan NetCDF ya kalau tidak salah, agak repot nih kalau di GIS. Oke, ada pertanyaan lagi dari Dr. Yesi dari Restek. Mudah-mudahan ini bukan pertanyaan ujian ya, karena Dr. Yesi kan sebagai ahli remote sensing lah. Apakah ada error akibat bayangan bukit atau gunung di datasar yang kemudian terdeteksi sebagai daerah banjir? Mungkin kalau boleh saya tambahkan, kalau kami dulu ya, waktu masih membantu Kang Sams di JIC, ketika terjadi banjir di Jakarta itu sulit sekali mendeteksi wilayah banjir. Nah ini bagaimana nih?
Sepertinya ada gangguan jaringan ya Pak Firman ya?
Ya, Pak Firman sepertinya aktif ya Bu.
Iya. Nah, apa saya coba menjawab dulu ya Bu Hana, mungkin nanti Bu Hana juga bisa menambahkan gitu. Iya, Bu Yesi. Untuk yang error akibat bayangan bukit atau gunung, memang dari SER itu kita ada kelemahan itu ya. Jadi bisa jadi yang seharusnya itu shadow gitu atau bayangan dideteksi sebagai banjir. Nah itu bisa ada beberapa metode begitu untuk mengatasinya. Bisa dengan mengeliminir menggunakan slope begitu ya. Jadi dari kemiringan biasanya kan kita anggap bahwa yang di area yang dengan kemiringan tertentu berarti itu bukan area genangan gitu. Atau bisa juga dengan menggunakan ada namanya itu hand. Saya lupa ininya, saya lupa panjangannya. Jadi hand itu semacam untuk mengetahui begitu data yang dekat dengan sungai gitu. Jadi nearest index gitu, dekat dengan sungai. Bisa dengan itu gitu. Itu kalau dari saya itu. Mungkin dari Bu Hana menambahkan.
Ya, betul. Betul sekali apa yang disampaikan Bu Filsa. Kita memang banyak kendala dan kelemahan juga ya Bu ya, maksudnya butuh proses lanjutan kalau menurut saya gitu. Tapi karena kami bergerak untuk quick response, jadi biasanya kami pengalaman saya pribadi biasanya kami memperoleh data-data lapangan juga, data lapangan dari BNPB atau BPBD terkait posisi latlong dari kejadian banjir itu yang biasanya membantu kami untuk memodifikasi algoritma atau threshold-nya itu sih Bu.
Menambahkan sedikit juga tadi terkait dengan Pak Firman yang menyebutkan untuk daerah perkotaan atau urban yang memang sangat lebih sulit begitu ya untuk mendeteksi banjirnya. Nah itu karena memang kan banyak gedung-gedung, jalan dan yang lain sebagainya, bayangan juga yang bisa diartikan sebagai banjir. Nah biasanya juga kita membutuhkan citra yang resolusinya lebih tinggi Pak, untuk bisa mendeteksi yang untuk daerah tersebut. Jadi meskipun misalnya menggunakan SAR pun harus yang resolusinya lebih tinggi kalau memang ingin fokus di daerah perkotaan itu. Kemudian juga nanti polarisasinya juga yang digunakan mungkin bisa ini ya, kan kalau misalnya biasanya kalau saya gitu ada beberapa juga yang pakai misalnya pakai co-polarization, cross polarization gitu, tapi banyak juga yang menggunakan co-polarization. Nah, kalau nggak salah di daerah perkotaan itu mungkin bisa lebih digunakan yang cross-nya gitu misalnya untuk menguji begitu apakah dia lebih baik karena kan dia berarti mengalami ini itu double bouncing gitu ya istilahnya kalau misalnya untuk sinyalnya dari SAR sendiri kalau daerah perkotaan gitu karena mengenai gedung-gedung dan bangunan yang ada di perkotaan. Terima kasih.
Terima kasih Bu Filsa. Kalau dari Lapan terkait tadi ya menggunakan machine learning dan menambah data dari lapangan itu bagaimana ya? Mungkin bisa dijelaskan Ibu Hana.
Ya Pak, sebetulnya untuk data lapangannya biasanya kami manual menggunakan software yang ada itu Pak. Jadi kami sedikit mungkin agak memvalidasi agar keakuratan atau ketepatan dari deteksi kami itu sudah tepat atau belum. Karena cukup penting juga untuk validasi itu pada saat kejadian quick response. Karena kan data valid itu, apalagi SAR yang disampaikan Bu Filsa tadi gitu kan, banyak juga kekurangan dan kita juga harus meng-compare dengan data-data yang ada.
Ya. Masih ada lagi? Kami undang rekan-rekan dari list atau dari narasumber yang sesi sebelumnya ya. Kebetulan saya tidak bisa ikut ya karena ada jadwal mengajar. Jadi kurang hafal siapa saja yang memaparkan mungkin ya. Mr. Patrick mungkin atau is there any question from our colleague?
Chat aja dari Pak
from list or Wasdi. Hasan?
So thanks a lot for these very interesting presentations. I just would like to add to the particular problem of urban flood mapping. So as it was shown in the presentations by Marco Chini this morning and in the demo by Ramona, so we have on VASDI one application dedicated to urban flood mapping, and we would be very interested in collecting also your feedback if this tool helps you to improve the classification of flooded areas in Jakarta and in other regions in Indonesia where the floods may happen. Because this was, of course, a problem we were facing for many years, so that you can quite easily map flooded areas outside of the cities, but you didn't know exactly where the water was standing inside the city. So this is basically our major development of the last couple of years, to have this tool based on interferometric coherence available on VASDI. And we would be very interested in getting your feedback on to see if this tool at least reduces this problem that you described.
Thank you, Patrick. Yes, from our experience, it's very difficult to detect urban flood. And although we had big flood in Jakarta, but when we process for Sentinel Asia or for IDC, we could not get a good result. So it would be interesting to know more about WASDI product, and then we can collaborate by providing the information from the ground.
Exactly.
Masih ada pertanyaan dari rekan-rekan yang lain karena kita masih punya banyak waktu ini 20 menit. Sayang sekali kalau tidak ada.
I have a question.
Okay.
Comment, brother.
Please.
Adi?
Yes. Yes, please, Dr. Mansoor.
Yeah, so thank you very much. I think very interesting presentation today. One of our experience with SAR data is in the urban area is always problem because of higher backscatter is coming during the flood. So we try to see how much it's increased from normal if there's a flood, how much backscatter increase in what are the areas. And we did some work in flood in Sri Lanka. It seems that if you have normal backscatter of an urban area from a dry time, and then you get the increased backscatter in the flood time, then you compare, and we find that the area which are increased backscatter is affected by flood. At least this will give you a good idea that these are the area flooded area flooded. And that is, I think, in terms of extent, it is quite good, but I think some bit of more research or some groundwork will be required, particularly validation. We did some validation in Sri Lanka. It turns out to be quite good, actually. But this is one area I think we all can look into it in future. Thank you.
Thank you, Dr. Mansoor. Ya, ini persoalan bersama ya. Mungkin kalau teknologi yang ada sekarang itu ketika terjadi satu kejadian banjir, kita bisa cepat ya mendeteksi. Dulu masih ada error, masih ada banyak kesalahan untuk mendeteksi di perkotaan. Sekarang sudah ada kemajuan algoritma yang dikembangkan oleh WASDI misalnya, atau yang sudah dicoba juga oleh GIC di Sri Lanka untuk mendeteksi banjir yang lebih akurat. Kalau saya pribadi, ya kalau saya berperan sebagai publik nih ya, sebagai masyarakat, itu kan yang penting, bukan penting ya, akan lebih bermanfaat ketika kita tahu kalau saat ini hujan, ya, hujan terus-terusan ya, kalau di Bogor mungkin dari pagi sampai malam begitu sampai ke pagi lagi. Nah, apakah mungkin terjadi banjir ya? Walaupun ini kita tidak terkaitan dengan deteksi banjir ya, tapi dari data-data yang sebelumnya apakah Lapan sudah mencoba ya memprediksi dari curah hujan anomali, kemudian dengan data-data sebelumnya wilayah-wilayah yang rentan terhadap banjir, apakah mungkin begitu? Mungkin sudah pernah dikaji begitu? Atau yang lebih sulit lagi adalah landslide, bukan landslide, flash flood ya, banjir bandang. Nah, untuk deteksi setelahnya juga susah ya, karena kan ada rentang 6 hari. Itu 1 hari saja sudah tidak kelihatan gitu. Nah, ini bagaimana, mungkin pernah dikaji teknik-teknik tersendiri? Ada 2 hal ya. Yang pertama prediksi, apakah mungkin begitu. Yang kedua, kalau misalnya terjadi banjir bandang, bagaimana kita mendelineasi wilayah-wilayah yang terdampak? Karena 1 hari itu sudah kering lagi. Nah, mungkin ada tanggapan dari ibu-ibu dan bapak-bapak.
I don't know how to raise the hand. I'm Paolo. Can you hear me?
Yes, please.
Okay. Can I start if you want? Obviously, I would like to have the opinion of the EU experts. From my point of view, this is a very interesting point. And the only thing that I can tell you that from the technological point of view, so from the WASD point of view at least, the only solution that we found to deal with flash flood is the most simple one: integrate a multiple source. You know what I mean? So use Sentinel-1 for sure, but also Sentinel-2. But maybe you are lucky, Sentinel-2 passed before. Then we are opening, we are not ready now. You have seen WASI, still not now, but in the next month, we are opening also to as many commercial data providers as possible. So from my technical point of view, the only solution we found is to have many different applications that can work with a different sensor and open to the most possible sources. This increases a lot the probability that you are lucky and you have one image in the right moment. That's my 2 cents from the IT point of view. I leave the floor to the expert about this.
Thank you very much, Paulo.
Iya,
Yes,
Pak.
I...
Iya, kalau boleh menambahkan Pak Firman juga.
Silakan.
Iya, terkait dengan flash flood gitu ya, mungkin bisa digunakan karena kalau nggak salah yang untuk banjir Kalimantan Selatan, meskipun itu bukan termasuk yang banjir yang hilangnya cepat gitu ya, tapi kalau yang di Kalimantan Selatan itu ada sebuah aplikasi gitu, bukan aplikasi ya, mungkin lebih ke kayak kumpulan dari laporan masyarakat gitu. Jadi datanya tuh laporan dari masyarakat, data kejadian banjir. Jadi masyarakat itu bisa lapor ke situ, bisa lapor ke semacam webnya atau aplikasinya gitu, bilang bahwa di titik ini terdapat banjir gitu. Nah, itu yang bisa kita gunakan sebagai data awal juga dalam pemetaan banjir gitu. Kalau nggak salah itu ini dengan BPPD Provinsi Kalimantan Selatan ada semacam aplikasi tersebut.
Ya, menyambung komentar dari Ibu Filsa. Sepertinya kalau di OSM kan ketika ada satu kejadian bencana mereka punya tasking ya, dan Lapan di sini punya tugas khusus ya dari Sentinel Asia atau dari IDC melakukan analisis. Nah, apakah di Lapan sudah ada platform begitu ya untuk seperti membuka tasking? Jadi Lapan menyediakan datanya sendiri, kemudian nanti kami sebagai volunteer ya, sebagai sukarelawan membantu melakukan digitasi. Seperti saya yang banyak nganggur ya, wah ini ada kejadian banjir, kemudian ingin beramal gitu, ingin beramal baik, saya bantu Lapan lah untuk melakukan analisis, karena kan SIM-nya banyak, datanya banyak, orangnya kan sedikit ya. Paling kan Ibu Hana, Pak Udi mungkin, kalau atau Mas Fajar, nah ini kan terbatas lah. Apakah sudah ada atau mungkin sudah didiskusikan solusi seperti itu?
Sedikit menjawab Pak, sebetulnya untuk ke arah situ sudah ada pemikiran, tapi mungkin ini masih dalam proses untuk membangunnya. Dan juga sebetulnya BNPB sendiri kan sudah ada platform itu sendiri, di mana masyarakat itu bisa ngetek mana aja ada kejadian, itu baik itu banjir, longsor, dan lain-lain. Itu sih Pak. Jadi kita lebih bekerja sama ke BNPB-nya.
Perlu juga dengan hot OSM mungkin ya?
Iya, betul
kan
Pak.
Hot OSM kan pasukannya banyak ya.
Betul Pak. Tadi mungkin izin menjawab juga yang terkait prediksi banjir dari data meteorologi. Sebetulnya Lapan, khususnya untuk Lapan di Bandung, telah provide informasi seperti itu, yaitu bisa diakses di portalnya Sadewa, di mana pada kejadian banjir di Januari awal 2021 ini, PSTA telah memberikan informasi bahwa akan terjadi banjir sekitar kapan gitu waktunya, karena curah hujan yang cukup tinggi dengan dari sisi meteorologinya, itu sih Pak. Kemudian tadi saya juga sekalian menjawab yang di pertanyaan Pak Syam ya, data Pleiades, betul. Lapan sudah tidak kerjasama lagi dengan Pleiades, jadi kami sekarang bekerja sama dengan Worldview. Datanya, saya jujur belum pernah menggunakan Pak data Worldview itu, jadi saya belum bisa menjawab bagaimana kualitasnya. Terima kasih.
Oke, mungkin ada Marco, please. So, Mr. Marco, please, you can.
Thanks. I want to add just something what has been said regarding urban area. I think, especially for flash floods, because the water doesn't stand much. If you don't have an acquisition, it's difficult to detect. But using the coherence that is quite sensitive to small changes, it can happen that even an image after the event, if, for example, some damages have been caused in urban area, also rubbles and other kind of changes, could be really change the coherence. Then even if the water is not there anymore, you can use maybe this feature to detect the presence of water that was standing there before. So I think it could be, and then of course, if you have sensors with multiple polarization, like Sentinel-1, the one from Copernicus, it's quite efficient because in urban area, the interaction between the signal and the building, it depends a lot on how they are oriented with respect to the sensor. So then I think a synergy between the two polarization, it's quite beneficial. Yeah.
Thank you, Marco. So it means we can use coherence analysis with Sentinel-1, but maybe it will be better if we use the higher temporal SAR data like Cosmos SkyMate. Of course, it comes with the consequence. We have to purchase if we don't have the license, maybe, or maybe it's not provided by the charter. As I know, the charter only provide the amplitude image, not the single complex image. But yeah, I think maybe Lapan can take this as a note, as the one of the institution responsible for mapping disaster in Indonesia using remote sensing technology. Pertanyaan berikutnya, mungkin kita tutup ya pertanyaan yang tadi ya. Ini terkait dengan pertanyaan dari Pak Arman Manalu, bahwa banjir itu diakibatkan dari perubahan tata ruang. Nah, ini memang konteksnya sudah lebih kompleks ya, bukan hanya remote sensing, tapi apa sih? Ada dua istilah ya, hidrologi, satu lagi hidro apa? Jadi yang terkait dengan civil engineering. Jadi kita perlu ada high resolution dam, kemudian manhole ada di mana, kemudian drainasenya bagaimana, ada tutupan lahannya bagaimana. Ini kan modeling yang yang kalau saya pribadi tidak mengerti lah caranya bagaimana. Nah, apakah memungkinkan nih? Jadi kita bukan hanya menggambarkan titik banjir saja atau genangan yang ada, tapi memprediksi. Kalau prediksi tutupan lahan kan sudah bisa ya, dari apalagi di ITS ada rekan yang membuat softwarenya sendiri ya untuk perubahan tutupan lahan ini. Itu ketika disimulasikan mungkin 10 tahun ke depan tutupan lahannya demikian, kemudian ada perubahan iklim, misalnya curah hujan yang tadinya sekian berubah menjadi berapa, kira-kira wilayah yang rentan ya, ini sudah kaitannya kepada mitigasi ya, sepertinya. Apakah sudah pernah dilakukan di ITS atau di Lapan? Silahkan Ibu Filsa, Ibu Hana, dan rekan dari Eropa.
Menjawab ya Pak Firman ya. Kalau untuk aplikasinya yang bisa diakses gitu ya, misalnya secara bebas gitu memang belum ada. Tapi untuk terkait dengan penelitian pemodelan banjir sendiri sudah sering dilakukan. Bahkan untuk yang model 3D-nya begitu bagaimana dengan tutupan lahan, terus nanti untuk dengan curah hujan kemudian dan lain sebagainya itu sudah ada, memang pemodelannya sudah ada. Tapi memang kalau untuk aplikasi begitu ya, itu yang belum ada kalau dari ITS. Jadi hanya berupa penelitian saja dan pemodelannya saja itu ada. Terima kasih.
Terima kasih Ibu Filsa. Ibu Hana mungkin?
Ya, terima kasih. Sebetulnya untuk banjir sendiri seperti menggabungkan hidrodinamika, hidrometeorologi dan semuanya tuh sudah sering dilakukan juga, tapi berbasis in-house, penelitian in-house. Sebetulnya keinginan terbesar kami itu bagaimana kejadian banjir ini dapat diaplikasikan. Sebetulnya di si Pandora tadi itu ada juga potensi banjir, yang dimana menggabungkan peta bahaya dari BNPB dengan data curah hujan dari Himawari dan kemudian data DEM. Akan tetapi karena betul kan tadi kata Pak Firman juga, kalau bicara banjir itu kompleks gitu kan. Kami melihat itu masih banyak errornya juga, Pak. Masih dalam proses pengembangan kami. Sebetulnya keinginan kami itu semua di Indonesia berapa potensi banjirnya, apalagi dengan skalanya yang skala tinggi 10.000 pinginnya gitu kan. Tapi karena kan keterbatasan juga, Indonesia itu terlalu unik gitu kalau menurut saya. Jadi setiap daerah tuh beda-beda gitu. Saat ini saya penelitian menggunakan frekuensi rasio untuk banjir. Pada satu daerah dengan daerah lain itu memiliki famous parameter yang berbeda. Beda juga, threshold-nya itu berbeda-beda juga. Itu yang menyulitkan kami bagaimana aplikasi untuk seluruh Indonesia itu diterapkan, tapi secara general untuk mewakili semua karakteristik yang ada di Indonesia. Itu. Mungkin dari saya, Pak Firman.
Ya, kalau tidak salah Google sudah menyediakan ya, atau Facebook ya, yang aplikasi ketika ada banjir, saya lupa. Mungkin lupakan saja karena
kalau di Google Earth Engine itu ada Pak, jadi langsung ketika ada banjir begitu bisa melihat apakah itu terkena di tutupan lahan apa begitu, apakah terkena di lahan pertanian atau tidak gitu. Tapi cuma kalau untuk yang prediksinya, nah itu saya belum melihat ya. Kalau untuk prediksi apalagi pemodelan yang bentuknya 3 dimensi gitu misalnya, itu belum terlihat ya. Yang 3 dimensi loh ya Pak kalau untuk aplikasi gitu. Terima kasih.
Okay, so I saw before Marco raise your hands. You still want to? Now Patrick is raising his hand. So Marco, Marco apakah masih hendak bertanya atau tidak? Karena tadi saya memberikan kesempatan kepada ibu-ibu, ladies first.
No, I want to. Sorry, I want, because I didn't see that my hand raised. And yeah, I want just to add that I agree that having higher resolution data it's an advantage, especially in urban area. But the main drawbacks is in general is that these acquisitions are quite sporadic. So then you don't have the reference image to compare, which is the normal condition, because they don't have the capability to acquire systematically a certain region. While, for example, maybe the images from Sentinel-1, although the resolution spatial is 20 meters, I would not underestimate the time sampling, because you have a huge amount of data, always acquired with the same characteristics, that it's kind of, you have like a kind of dimension more, because the time, I would not underestimate the time, especially if you have to deal what was mentioned before with rice field and so on, because you have information also on the evolution of water during time with this kind of application. But of course, I agree that higher resolution data would be an advantage, but then you have to combine with the images acquired with different modes and not closing time.
Thank you, Marco, for your insight. And I will give the chance for Mr. Patrick.
Yes, thank
Do
you.
Have any? Yeah.
Yeah, I wanted also to mention that we are working on how we can improve the predictions or the uncertainty, how we can reduce the uncertainties of predictions using satellite Earth observation data. So very often, as it was described by Paolo, it's of course good to have multiple remote sensing images, but even in the ideal case, you will not have continuity of monitoring. So whereas a hydrodynamic model can make you a prediction that is continuous in time and space. So what we are working on is that we use the satellite data to control our model. So whenever you have a satellite image, you compare it to your model results and you do some corrections in your model. And we could show that by doing this systematically, we can also improve then the predictions over several time steps. So this combination of hydrodynamic modeling plus remote sensing, that's what also gives very good results in for improving predictions.
Yeah, thank you very much, Patrick. I think it's a very good opportunity for us to have a discussion in this event, so we can, I think, in the future. And you also already mentioned in the chat that you're open for further discussion, because this is for myself, I think it's something new, and maybe also for Lapan, and also Ibu Filsa will be very much interested in doing this kind of research. So yeah, I think it's very good opportunity for us to maybe in the future we can have tighter collaboration, because as explained by both resource person, that Indonesia, the flood in Indonesia are major. More than 25% of the disasters in Indonesia are floods. So it happens maybe in every month in Indonesia, and we don't have a rainy season anymore. All years are rainy season, so it will be very much interested. Oke, sekarang kita sudah sampai ke 5:30 ya. Sepertinya kita harus akhiri diskusi kita hari ini. Namun sebelumnya mungkin masih ada yang penasaran, masih ada yang ingin bertanya atau berkomentar. Ya, apabila tidak ada pertanyaan, mungkin pernyataan. Oke, kalau ini dari jauh hari ya.
Okay, a very quick comment on the last thing you said. I mean, I would like to point out that for me, for sure, I would like to say that this is a big opportunity also for us, the opportunity to collaborate with you, because I know, I see your expertise, different methodologies, different tools, and so was just a quick comment. Thank you for all this time, all this info, and I really consider this a big opportunity also for us to understand the requirement around the world, to deal with real life problems. So thank you again for this opportunity and this time. That was my quick comment.
Terima kasih, Paulo. Ya, sekali lagi kami ucapkan terima kasih kepada narasumber, kepada resource person dari ITS, dari LAPAN, dari LIST, dari WASDI, dan Bapak Ibu semuanya yang sudah bertahan ya, menyimak sampai sore hari ini. Mudah-mudahan apa yang kita diskusikan ini bermanfaat ya, terutama bagi bangsa dan negara ya, bagi Indonesia, di mana kita sama-sama tahu banyak bencana, dengan bagaimana kita menggunakan ilmu dan teknologi ini untuk meminimalisir ya, bencana, meminimalisir dampak yang terjadi. Oke, kita tutup dengan alhamdulillahirrahmanirrahim. Terima kasih sekali lagi. Kami kembalikan kepada Ibu Nancy sebagai MC ya. MC dadakan, jangan-jangan sekali. Kalau kemarin kan dadakan ya.
Terpaksa.
Sekarang sudah terlatih. Sudah punya pengalaman.
Ya, makin
Ya.
enjoy. Baik, terima kasih Pak Adi. Memang sepertinya hari ini justru diskusinya paling menarik karena peserta masih bertahan dan diskusi bisa narasumber dari internasional dan narasumber dari Indonesia bisa saling diskusi gitu ya Pak. Semoga masih sisa 2 hari kita bisa mempertahankan ritme yang seperti ini gitu ya Pak. Ya, baik, saya ucapkan terima kasih kembali. Masih ada 60 peserta yang bergabung dan kami harap besok juga akan lebih banyak lagi. Bapak dan Ibu sekalian, demikianlah acara pada hari ini. Besok kita masih akan melanjutkan untuk tema selanjutnya yaitu water use and crop, pemanfaatan pengendalian jauh dalam mendukung pertanian. Untuk acara besok masih menggunakan link Zoom yang sama dan masih disiarkan secara langsung melalui YouTube PUSFATJA LAPAN. Sekali lagi, saya selaku MC mewakili seluruh panitia, kami memohon maaf apabila ada kesalahan. Kami pamit undur diri, sampai bertemu besok kembali. Wassalamualaikum warahmatullahi wabarakatuh. Selamat sore, tetap jaga kesehatan dan patuhi protokol kesehatan. Salam sehat. Sampai jumpa.